So, here's something worth thinking about as you settle in tonight. Every source of energy that humans have ever used, every single one, until about 80 years ago, was something you could see. Fire, obviously. You could watch it dance on a torch, feel it on your skin, smell the smoke curling off the wood. Wind. You could see the sails billow, the branches sway, the dust kick up across the field. Water. You could hear it roaring through a mill race, watch it churn white against the stones. Even coal, even oil, even natural gas, when you burned them, there was flame. There was heat you could feel. There was light you could see. There was smoke or steam or exhaust rising into the sky. For 300,000 years, every time a human being harnessed energy, there was something visible happening. Something obvious. Something your eyes and your hands and your nose could confirm. And then, in the middle of the 20th century, something changed. Someone figured out how to release the energy locked inside the nucleus of an atom. And for the first time in all of human history, we had a source of energy that was completely, utterly, profoundly invisible. You cannot see a neutron. You cannot hear a chain reaction. You cannot feel radiation, not until it's too late. You cannot smell fission products until they've already escaped containment. If you stood next to a working nuclear reactor behind the proper shielding, you would see nothing. You would hear nothing remarkable. You would feel nothing unusual. Just a building, just concrete and steel, maybe a faint hum from the turbines down the hall. And yet, inside that building, atoms are splitting, releasing energy that was locked away since before the Earth existed, energy that was forged in the death throes of ancient stars billions of years ago. And that energy is boiling water and spinning turbines and pushing electricity through copper wires and into the grid that keeps the lights on in hospitals and homes and schools. Right now, tonight, as you lie here. The whole thing is invisible. The fuel doesn't burn, the reaction doesn't glow. The danger has no color, no taste, no texture. And maybe that's why nuclear energy is the most feared, the most misunderstood, and the most argued about source of power that humans have ever discovered. Because every instinct we have, every survival mechanism that evolution spent millions of years building into our nervous system, depends on being able to see danger, to hear it, to smell it. Fire is dangerous, and fire looks dangerous. A rushing river is dangerous, and it sounds dangerous. A predator is dangerous, and you can see it coming. But radiation is silent. It's invisible. It passes through walls and skin and bone without announcing itself. And something deep in our brains, something ancient and pre-verbal, rebels against the idea of trusting a force we cannot perceive. And yet, 440 reactors are running tonight in over 30 countries, generating roughly 10% of the world's electricity. Quietly, steadily, invisibly. And the story of how we got here, how humans discovered an invisible fire, learned to light it, learned to control it, learned to fear it, learned to build instruments that could see what our eyes never could. That story is one of the strangest and most beautiful in all of science. Because it's a story about trust, about learning to trust what you cannot see, about building layer after layer of technology and engineering and institutional discipline, all of it designed to manage a force that your senses cannot detect. So tonight, let's walk through it, slowly, from the very beginning. How did we discover that there was energy hidden inside the atom? How did we figure out that this energy could be released? How does a nuclear reactor actually work, step by step, piece by piece? And how did we learn to see the invisible, to build eyes where evolution gave us none? If you drift off somewhere along the way, that's perfectly fine. This story has been unfolding for over 100 years. It can wait for you. There's no rush. Just settle in. Let the ideas come to you, and we'll see where the night takes us. Let's start with what came before. Because to really understand what makes nuclear energy so strange, so unsettling, so fundamentally different from everything else, you have to understand what energy looked like for all of human history up until the moment someone cracked open the atom. And for most of that history, energy looked like fire. Think about how long fire has been with us. The earliest evidence of controlled fire use goes back somewhere around 1 million years, give or take a few 100,000, depending on which archaeological sites you trust. That's an almost incomprehensible stretch of time. For 1 million years, humans and our ancestors sat around fires, cooked food over fires, stayed warm through cold nights because of fires. Fire was the original technology. It was the first time a living creature took a natural process and bent it to its will. And the important thing about fire, the thing that matters for our story, is that fire is the most visible thing in the world. You can see it from miles away in the dark. You can feel its heat on your face from across a room. You can hear it crackle and pop as the wood breaks apart. You can smell the smoke for hours after it's gone out. Fire engages every sense you have. And because of that, your relationship with fire is deeply intuitive.
You know, without anyone teaching you that the bright orange part is hot and the dark part is cooler. You know that if you get too close, you'll burn. You know that if the wind picks up, the fire might spread. You know that if you stop feeding it fuel, it will die. All of this knowledge is available to you through your senses, directly, immediately, without any instruments or training or abstract reasoning. And that intuitive relationship with visible energy shaped everything that came after. When humans started building machines to harness energy, those machines were visible too. The first real energy revolution, the one that changed the world more than any other before the atom, was the steam engine. And the steam engine is a spectacularly visible machine. You can watch the fire burn under the boiler. You can see the water turn to steam, billowing out in great white clouds. You can hear the piston hammering back and forth. Ka-chonk, ka-chonk, ka-chonk. Rhythmic and loud and mechanical. You can feel the heat radiating off the boiler from 10 feet away. You can see the great beam rocking up and down like a giant breathing. 12 strokes a minute, slow and ponderous and powerful. Thomas Newcomen built the first practical steam engine around 1712, and it was used to pump water out of coal mines in England. The thing was enormous, loud, and almost absurdly inefficient. It consumed vast quantities of coal to do relatively little work. But it worked. And the reason people trusted it, the reason they were willing to invest money in it and put workers near it, was that you could see exactly what it was doing at every moment. The fire was right there. The steam was right there. The piston was right there, going up and down, up and down. If something went wrong, you could see it. If the boiler was getting too hot, you could feel it. If pressure was building dangerously, you could hear the metal groaning. Your senses told you everything you needed to know. James Watt improved the steam engine in the 1760s and 70s, and his improvements made it vastly more efficient. But they didn't change the fundamental nature of the thing. It was still fire, water, steam, piston. Still visible, audible, tangible. Still something you could understand by looking at it. And when the steam engine went on to power the Industrial Revolution, when it drove the locomotives and the factories and the mills and the ships that transformed the world in the 1800s, all of that transformation was visible. You could see the smokestacks, you could hear the engines, you could feel the vibration of the machinery through the floor. The entire energy system of industrial civilization was something you could perceive with your body.
Even electricity, which arrived in practical form in the late 1800s, was at least partly visible. You couldn't see the current flowing through a wire, true, but you could see the sparks when wires touched. You could see the glow of an incandescent bulb. You could feel the shock if you touched a live connection. And the generators that produced electricity were themselves driven by visible forces. Steam turbines heated by coal fires, or water turbines spun by rivers rushing through dams. The invisibility of electricity was, in a sense, only skin deep. If you followed the wires back to their source, you always found something you could see. A fire burning, water falling, a turbine spinning, something tangible at the root of it all. And that is the world that existed right up until the very end of the 19th century. A world where energy was visible, where power came from processes that your eyes and ears and hands could confirm. Where trusting a machine meant watching it work and seeing for yourself that it was doing what it was supposed to do. And there's something else about visible energy that's worth mentioning. Something so obvious that we rarely stop to think about it. Visible energy gave us metaphors. Our entire language of power and energy is built on things we can see. We talk about a spark of genius, a flame of passion, burning ambition, being fired up, having fuel for an argument, building up steam, hitting things with full force. Every single one of these metaphors comes from visible, tangible energy sources. Fire, steam, water, wind, force. When nuclear energy arrived, it brought no metaphors. There is no common figure of speech based on fission. We don't say someone has a nuclear personality to mean they're energetic, although going nuclear has come to mean losing control. An interesting choice that reveals our deep unease with the technology. The language we use to describe nuclear energy is borrowed from other domains. We talk about the chain reaction of events, about things reaching a critical mass, about situations melting down. But these phrases describe failure, not function. We have no everyday language for what a nuclear reactor does when it's working properly, because what it does when it's working properly is invisible. And this linguistic gap matters more than you might think. Language shapes thought. If we have no words for the normal, healthy operation of nuclear energy, if our only nuclear metaphors are about catastrophe, then our mental picture of nuclear energy is inevitably skewed toward catastrophe. We think of Chernobyl when we think of nuclear energy, the way we'd think of plane crashes if we had no word for flight. The invisibility of the process deprives us of the sensory experiences that would normally generate positive metaphors. And in the absence of those metaphors, the negative ones dominate. This is one of the quiet tragedies of the invisible fire. It works so well, so quietly, so reliably, that it generates no stories. The 400+ reactors operating worldwide tonight are producing roughly 10% of the world's electricity without any drama whatsoever. No explosions, no meltdowns, no heroic interventions, just quiet, steady, invisible work. But everything worked fine today is not a story, it's not a headline, it's not a metaphor. And so, the invisible fire disappears into the background of the world, noticed only when something goes wrong, invisible in its success, and visible only in its failure. And maybe that's the ultimate expression of its invisibility. The better it works, the less we see it. The safer it operates, the less we think about it.
The more reliably it delivers power, the more completely it vanishes from our consciousness. The invisible fire is invisible not only in its physics, but in its sociology. It is invisible in its triumphs and visible only in its disasters. And that asymmetry shapes every public conversation about nuclear energy in ways that are profoundly misleading. But then, in 1896, in a laboratory in Paris, a man named Henri Becquerel put a piece of uranium in a drawer, and everything began to change. Because what Becquerel found in that drawer was the first hint of an energy source that was completely, fundamentally, stubbornly invisible. An energy that didn't burn, didn't glow, didn't make a sound. An energy that was just there, silently radiating from the heart of matter itself, as if the atoms had a secret they'd been keeping for billions of years. And that secret was about to rewrite the rules of everything. To understand what Becquerel stumbled onto, you need to understand what the scientific world looked like in the 1890s. And honestly, the mood was a little bit smug. There was a widespread feeling, especially among the older generation of physicists, that the big questions had mostly been answered. Newton had given them mechanics and gravity. Maxwell had unified electricity and magnetism into one gorgeous set of equations. Thermodynamics was well understood. The periodic table was filling in nicely. There was a famous sentiment, sometimes attributed to Lord Kelvin, that physics was essentially complete, that all that remained was to measure things to a few more decimal places. The grand architecture was done. They were just polishing the furniture. That turned out to be spectacularly wrong, and the cracks were already showing. In 1895, a German physicist named Wilhelm Röntgen was doing something that physicists of his era loved to do, which was running electrical current through glass tubes with most of the air pumped out. These were called cathode ray tubes, and they were a popular toy in physics laboratories of the time because they produced interesting glowing effects. Röntgen noticed something strange. A fluorescent screen across the room was glowing, even though it was too far from the tube to be hit by the cathode rays themselves. Something invisible was coming out of that tube, passing through solid objects and making the screen light up on the other side of the room. He called them X-rays because he didn't know what they were. The X was literally for unknown. And when he put his wife's hand between the tube and a photographic plate and produced an image of her bones, her actual bones, visible right through her flesh, the world went a little bit crazy. That image was published everywhere. It was one of the first viral sensations in the history of science. People were amazed, thrilled, and more than a little unsettled. Here was an invisible ray that could pass through solid matter and reveal what was hidden inside. The implications were both exciting and deeply strange. But what Röntgen's discovery really did, beyond the immediate sensation, was kick off a frenzy of investigation. If invisible rays could come out of an electrical tube, what else might be out there? What other invisible things were lurking in the world, undetected, waiting to be found? And that question led almost immediately to Henri Becquerel. Becquerel came from a family of physicists. His father and grandfather had both been professors of physics in Paris. He was, in many ways, a scientist of the old school, careful, methodical, perhaps a bit cautious. When Röntgen announced his X-rays, Becquerel wondered whether certain minerals might naturally emit similar rays after being exposed to sunlight. He knew that some minerals, particularly those containing uranium, would glow faintly after being left in the sun, a phenomenon called phosphorescence. Maybe, he thought, that glow included X-rays. Maybe sunlight was energizing the uranium enough to produce invisible radiation. His experimental plan was straightforward. He would take a uranium salt, a compound containing uranium,
place it on top of a photographic plate wrapped in thick black paper, and leave the whole thing out in the sun. If the uranium was emitting X-rays or something like them, those rays would pass through the black paper and fog the photographic plate, creating an image. The black paper was important because it blocked visible light, so any fogging of the plate would have to be caused by something invisible, something that could penetrate where light could not. He tried it and it worked. After a few hours in the sun, the photographic plate showed a clear shadow of the uranium salt. Something invisible had passed through the paper and affected the plate. Becquerel was pleased but not particularly surprised. This was, after all, exactly what he'd predicted. The uranium was absorbing sunlight and re-emitting it as invisible radiation. A neat result, consistent with existing physics, nothing to lose sleep over. And then the weather intervened. The last week of February 1896, Paris was overcast. Grey clouds, no sun. Becquerel had prepared his next experiment, uranium salt sitting on a wrapped photographic plate, ready to go. But there was no sunlight to energize the uranium. So he put the whole setup in a drawer and waited for the clouds to clear. A few days later, for reasons that aren't entirely clear, maybe he was tidy, maybe he was impatient, maybe he just wanted to check, he decided to develop the photographic plate anyway. He expected to see perhaps a very faint image, or more likely nothing at all, since the uranium hadn't been exposed to sunlight. Without the sun's energy, the uranium shouldn't have been emitting anything. Instead, the image was strong, clear, sharp, just as intense as the ones he'd gotten after hours of direct sunlight, maybe even more so. Think about what that means. The uranium had been sitting in a dark drawer, no sunlight, no external energy source of any kind, just a chunk of mineral sitting in the dark, quietly, invisibly, relentlessly emitting some kind of radiation that passed through black paper and fogged a photographic plate. The energy wasn't coming from the sun. The uranium wasn't re-emitting something it had absorbed. The radiation was coming from the uranium itself, spontaneously, continuously, without any outside input at all. And here is the moment that matters for our story.
Because Becquerel had just discovered something that had never been seen before in the history of science. He had found a source of energy that was completely invisible, that required no fuel, no spark, no flame, no external force. The uranium was just sitting there, radiating. Where was the energy coming from? Nobody knew. It wasn't a chemical reaction. It wasn't heat. It wasn't electricity. It wasn't magnetism. It wasn't any known physical process. The uranium was doing something that the physics of the 1890s simply could not explain. Something invisible was pouring out of ordinary matter, without being triggered, without being sustained, without any apparent source. As if the atoms themselves were slowly, quietly, invisibly leaking energy that had been stored inside them since they were formed. Becquerel published his findings, but he was, characteristically, cautious and measured in his claims. He described what he had observed without making grand theoretical pronouncements. He was a careful man, and careful men don't rush to conclusions. But someone else was about to take his quiet little discovery and run with it, harder and further and more dangerously than anyone could have imagined. Her name was Marie Curie, and she was about to pick up the invisible fire with her bare hands. Marie Skłodowska was born in Warsaw in 1867, at a time when Poland didn't officially exist as an independent country. It was carved up between Russia, Prussia, and Austria, and the Russian partition, where Warsaw sat, was a place where Polish culture and language were actively suppressed. Higher education for women was forbidden. If you were a young Polish woman with a burning desire to study science, your options at home were essentially zero. So Marie did what many ambitious young Poles of her generation did. She went to Paris. She enrolled at the Sorbonne in 1891, one of a small number of women in the science faculty, and she threw herself into physics and mathematics with an intensity that impressed even her professors. She lived in a tiny apartment in the Latin Quarter, sometimes too absorbed in her studies to remember to eat. She later recalled that entire weeks passed where she survived on bread, chocolate, and tea. She was brilliant, driven, and working under conditions that would have stopped most people cold. She met Pierre Curie in 1894. Pierre was already an accomplished physicist, known for his work on magnetism and crystallography. He was quiet, thoughtful, deeply principled, the kind of scientist who cared more about understanding nature than about fame or money. They married in 1895, and the partnership that followed became one of the most productive and most tragic in the history of science. When Becquerel published his results on the invisible radiation from uranium, Marie saw an opportunity. She needed a subject for her doctoral thesis, and this strange new phenomenon, barely explored, wide open, seemed perfect. She began systematically testing every element she could get her hands on, measuring the invisible radiation using an electrometer that Pierre and his brother had invented. The electrometer was a sensitive device that could detect the tiny electrical currents produced when radiation ionized the air around it. It was, in effect, one of the first instruments designed to make the invisible visible, to translate an imperceptible phenomenon into a number on a dial that a human being could read and record. Marie's approach was methodical and exhausting. Element after element, compound after compound, she measured the radiation. Most things gave off nothing. Uranium did, as Becquerel had shown. And then she found that thorium was also radioactive, a discovery she made independently of Gerhard Schmidt, who found the same thing around the same time in Germany. But then she noticed something puzzling. A uranium ore called pitchblende was significantly more radioactive than pure uranium itself. Much more. More than any known uranium compound could account for. This was strange. If the radiation was coming from the uranium atoms, then pure uranium should be more radioactive than an ore that contained uranium mixed with other stuff. The ore should be less radioactive, not more. Unless there was something else in the pitchblende, something unknown, something that was even more powerfully radioactive than uranium, something that nobody had discovered yet. Marie Curie had a hypothesis, and it was a bold one. She believed that pitchblende contained a new element, an element so rare that it had never been detected by conventional chemistry, but so intensely radioactive that even a tiny amount of it could dominate the radiation signature of a large sample of ore. And this is where the story becomes physically grueling, in a way that's hard to overstate. The Curies decided to find this element by processing pitchblende ore and systematically separating it into its component parts, testing each fraction for radioactivity and chasing whichever fraction was most active. It was like searching for a needle in a haystack, except the needle was invisible, and the only way to find it was to dissolve the haystack, separate it into piles, measure each pile with a finicky electrometer, and then dissolve the hottest pile again, and repeat. They worked in a converted shed, a leaky, unheated former dissecting room at the school where Pierre taught. Pierre Curie later described it as a cross between a stable and a potato shed. It had no proper ventilation, no proper flooring, and a glass roof that leaked when it rained.
which in Paris is fairly often. In summer it was stifling, in winter it was freezing. And in this space, Marie would spend entire days stirring massive vats of boiling, chemically treated pitchblende ore with an iron rod almost as tall as she was. The work was backbreaking. They were processing tons of ore, literally tons, because the elements they were looking for were present in such minuscule quantities that you needed enormous amounts of raw material to isolate even a trace. Think about that. Tons of rock, ground up, dissolved in acid, boiled, filtered, precipitated, dissolved again, separated, measured, and then the most radioactive fraction taken and the whole process repeated, over and over and over, month after month after month, in a leaky shed in Paris.
And at the end of it, from all those tons of raw material, they isolated tiny amounts of two new elements. The first they named polonium, after Marie's homeland. The second they named radium. And radium was extraordinary. Here's where the invisibility of radioactivity does something paradoxical. Because radium was so intensely radioactive, so ferociously energetic at the atomic level, that it did something no other radioactive substance did in such dramatic fashion. It glowed. A tiny vial of radium salt, sitting on a shelf in a dark room, would emit a faint, eerie blue-green light, all on its own, endlessly, as if it contained some inexhaustible inner fire. In the darkness of the Curie's shed, radium literally made itself visible. The invisible energy was so concentrated, so intense, that it forced its way into the visible world. And people were mesmerized. Radium became a sensation. It was exhibited at scientific conferences and stared at in wonder. Marie and Pierre would sometimes bring vials of radium salts home and watch them glow in the dark. Pierre once carried a vial in his waistcoat pocket for an extended period to demonstrate its properties to colleagues, and developed a painful burn on his skin beneath where the vial had rested. He noted the burn with scientific curiosity, recording how long it took to heal, treating it as a data point rather than a warning. The Curies won the Nobel Prize in 1903, shared with Becquerel, for their work on radioactivity. Marie would win a second Nobel in 1911, this time in chemistry, for isolating radium and polonium. She remains the only person ever to win Nobel Prizes in two different sciences. But here's the thing that haunts this story, the thing that makes it a perfect illustration of why invisible energy is so dangerous. Neither Marie nor Pierre nor anyone else at the time understood what the radiation was actually doing to their bodies. They couldn't see it. They couldn't feel it, except as occasional skin burns that seemed minor and temporary. Marie carried vials of radioactive material in her pockets. She kept samples on her desk, on her nightstand. Her lab notebooks from that era are still so radioactive that they're kept in lead-lined boxes at the Bibliothèque Nationale de France, and if you want to examine them, you have to wear protective gear and sign a liability waiver acknowledging the risk. Pierre Curie was killed in 1906, struck by a horse-drawn cart on a rainy Paris street, his reflexes perhaps already slowed by years of radiation exposure, though we can't know that for certain. Marie continued the work alone, and for nearly 3 more decades, she continued to handle radioactive materials with minimal protection, continued to breathe radioactive dust, continued to let the invisible energy wash over her day after day after year after year. She died in 1934 of aplastic anemia, a disease in which the bone marrow stops producing blood cells properly. The cause was almost certainly decades of cumulative radiation exposure. The invisible fire she had discovered, the invisible fire she had held in her hands, had been slowly, quietly, invisibly destroying her from the inside.
And this is the profound lesson that the story of Marie Curie teaches us, a lesson that would echo through the entire history of nuclear energy. Invisible things can hurt you. Invisible things can kill you. And the most dangerous form of ignorance is not knowing that something is happening to you at all. Fire burns, and you pull your hand away. Radiation burns, but by the time you feel it, the damage is already deep. The human body has no radiation detector. Evolution never built one, because in the natural world, at the radiation levels our ancestors encountered, it simply wasn't necessary. We had no need for such a sense. And when we suddenly found ourselves handling materials that were millions of times more radioactive than anything in the natural environment, we were profoundly, dangerously blind. And this raises a question that matters deeply for the rest of our story. What exactly was the radiation that killed her? What was coming out of those atoms? Because it turned out that the invisible fire wasn't one thing. It was three different things, each invisible in its own way, each dangerous in its own way. And understanding the difference would become the foundation of everything that came after. When Becquerel discovered radioactivity and the Curies isolated radium, the immediate question was, what is this radiation exactly? It was invisible, it could penetrate solid matter, it fogged photographic plates, and it made the air electrically conductive. But what was it made of? What was coming out of those atoms? The answer, as Rutherford and others gradually worked out, was that there were three different kinds of radiation, each with profoundly different properties, and each invisible in its own way. Alpha radiation turned out to be composed of particles, each one consisting of 2 protons and 2 neutrons bound together, essentially a helium nucleus traveling at roughly 5% of the speed of light. Alpha particles are relatively heavy and relatively slow by nuclear standards, and they interact strongly with matter. They can be stopped by a sheet of paper or by the outer layer of dead skin on your hand. If alpha-emitting material stays outside your body, it is essentially harmless. You could hold a piece of polonium in your hand and the alpha particles wouldn't penetrate your skin. But if alpha-emitting material gets inside your body, through inhalation or ingestion or a wound, the story changes completely.
Now the alpha particles are being emitted directly into living tissue, with no dead skin layer to stop them. Each alpha particle dumps all its energy into a tiny volume of tissue, causing intense, concentrated damage to cells and DNA. This is why radon gas, a naturally occurring alpha emitter that seeps out of certain rocks and soils, is the second leading cause of lung cancer after smoking. The radon itself is harmless on your skin, but breathe it in and the alpha particles tear through the delicate tissue of your lungs. Beta radiation consists of electrons, or in some cases positrons, ejected from the nucleus at high speeds, sometimes approaching the speed of light. Beta particles are much lighter than alpha particles and can penetrate further into matter, traveling through several feet of air and through thin layers of clothing or skin. They can cause skin burns if the exposure is intense enough, as the Curies discovered, but they are still stopped relatively easily by denser materials. A thin sheet of aluminum, a thin sheet of lead, or a pane of glass. Gamma radiation is the most penetrating of the three. Gamma rays are not particles at all, but electromagnetic waves, the same fundamental phenomenon as light and radio waves and X-rays, but with much higher energy and correspondingly much shorter wavelength. Gamma rays can pass through the human body, through walls, through most construction materials. Stopping them requires dense, heavy shielding, thick lead, concrete, or water. What makes this trio so treacherous is that they are all invisible, but invisible in different ways and dangerous in different ways. An alpha source that is harmless at arm's length can be lethal if inhaled. A beta source that causes only skin burns from the outside can cause deep tissue damage if ingested. A gamma source can harm you from a distance, through walls,
without you knowing it's there. And here is the deepest challenge of radiation protection. You cannot generalize. You cannot say, radiation is dangerous, and leave it at that. Because the danger depends entirely on the type of radiation, the distance from the source, the duration of exposure, and whether the source is outside or inside your body. A comprehensive radiation protection program must account for all of these variables, and it must do so for every person, in every location, at every moment, in a facility where the radiation sources are constantly changing as the reactor operates, as fuel is loaded and unloaded, as waste is processed and stored. This is why nuclear facilities have health physics departments, staffed by specialists whose entire job is to track, measure, and manage radiation exposure. Health physicists carry dosimeters that record their cumulative exposure. They use portable survey meters to measure radiation fields before entering work areas. They set up air samplers to monitor for airborne radioactive particles. They analyze wipe samples from surfaces to check for contamination. Every task that involves potential radiation exposure is planned in advance, with dose estimates calculated and protective measures specified. Workers wear personal dosimeters that are read out regularly, and their cumulative lifetime dose is tracked in a permanent record. All of this infrastructure, all of these instruments and procedures and specialists exists because the danger is invisible. In a chemical plant or a steel mill, workers can often see or smell or feel the hazards they face. The heat of molten metal, the fumes of toxic chemicals, the noise of heavy machinery. In a nuclear facility, the primary hazard has no sensory signature whatsoever. The only defense is measurement, and the only way to measure is with instruments that convert the invisible into numbers that human beings can act on. This reality, the absolute dependence on instruments for safety-critical information, creates a special kind of responsibility. If a thermometer in a kitchen is slightly inaccurate, the worst outcome is an overcooked meal. If a radiation detector in a nuclear facility is inaccurate, the consequence could be a worker receiving a dose that will cause cancer 20 years later. The calibration, maintenance, and testing of radiation monitoring instruments is therefore subject to extraordinarily rigorous standards. Every detector is tested against known radiation sources at regular intervals. Every calibration is documented. Every anomaly is investigated. And even with all of this, uncertainties remain. Radiation dose is not something you can measure with the precision of, say, a temperature. Dose is an estimate based on measurements of radiation fields and assumptions about how those fields translate into energy absorbed by human tissue. Different types of radiation have different biological effects, and these differences are accounted for by weighting factors that convert physical dose, measured in grays, into effective dose, measured in sieverts. The weighting factors themselves are based on decades of epidemiological studies, primarily of Japanese atomic bomb survivors, and they carry their own uncertainties. The point is not that radiation protection is unreliable. On the contrary, it is one of the most well-developed and well-validated fields of occupational health. The point is that everything in nuclear radiation protection is one step removed from direct perception. Every number is a translation. Every measurement is an inference. Every safety margin is a judgment call based on the best available science, applied to a hazard that no human being can directly sense. The invisible fire demands not just technology, but epistemic humility. The recognition that what we know is always filtered through instruments, that our knowledge is always mediated, always indirect, and that the margin between safety and danger lies in the quality of that mediation. And that recognition, uncomfortable as it is,
may be one of the most important things that nuclear energy has taught us about ourselves. We are not creatures of direct perception alone. We are creatures who can build instruments to extend our perception, who can construct institutions to maintain our vigilance, who can develop systems of knowledge that allow us to manage forces far beyond the reach of our senses. The invisible fire has forced us to confront the limits of our biology and to build, through science and engineering and institutional discipline, a new kind of vision. A vision made not of light and optic nerves, but of Geiger counters and dosimeters and neutron flux monitors and thermocouples and computer models and regulatory frameworks and safety cultures and shared knowledge accumulated over decades. A vision of the invisible, built by a species that, until very recently, could only see what was in front of its face. But what exactly was the radiation? Where was the energy coming from? Why were these atoms leaking energy at all? Becquerel had detected the phenomenon. The Curies had isolated the most active elements, but none of them could explain what was actually happening inside the atom. To answer that question, someone was going to have to look deeper, deeper than anyone had ever looked before, into the heart of matter itself.
And the person who did that, who first peered into the atom and saw what was hiding there, was a loud, brash New Zealander with a booming voice and an appetite for scientific combat. His name was Ernest Rutherford, and what he found inside the atom would change the world forever. Ernest Rutherford was, by all accounts, the kind of person who dominated every room he walked into. Big personality, big voice, enormous energy. He was born in New Zealand in 1871, the fourth of 12 children in a family of modest means. He won a scholarship to Cambridge, arrived in England in 1895, and almost immediately began doing work that would reshape physics. Rutherford was fascinated by the invisible radiation that Becquerel and the Curies had discovered, and he set about studying it with the energy and directness that characterized everything he did.
Within a few years, he had figured out that there were at least two different kinds of radiation coming from radioactive materials. He named them with characteristic simplicity, alpha and beta, after the first two letters of the Greek alphabet. Alpha rays were relatively heavy, positively charged particles that could be stopped by a sheet of paper. Beta rays were lighter, negatively charged, and could penetrate further, through thin metal but not through thick lead. Later, a third type of radiation was identified by the French physicist Paul Villard, gamma rays, which were not particles at all, but a form of electromagnetic radiation, like light or X-rays, but with far more energy. Gamma rays could pass through most materials and required thick lead or concrete to block them. Three types of invisible emission from a single atom, each with different properties, each capable of passing through matter in different ways, none of them detectable by any human sense.
But Rutherford's greatest contribution wasn't just cataloguing the radiation. He wanted to know what the atom itself looked like. What was its internal structure? Where was the radiation coming from? And to answer that question, he designed one of the most famous experiments in the history of physics. The prevailing model of the atom at the time had been proposed by J.J. Thomson, who had discovered the electron in 1897. Thomson imagined the atom as a sort of plum pudding, a ball of positively charged material with negatively charged electrons scattered through it like raisins in a pudding. A smooth, uniform blob of stuff. If this model was correct, then firing particles through an atom should be like shooting a bullet through a cloud. Everything should pass through with only slight deflections, because there would be nothing particularly dense in there to deflect it. Rutherford tested this by using alpha particles as tiny projectiles, firing them at a very thin sheet of gold foil and seeing what happened. The experiment was actually carried out by his colleagues Hans Geiger and Ernest Marsden, working under Rutherford's direction, in Manchester around 1909. And most of the alpha particles did exactly what the plum pudding model predicted. They passed straight through the gold foil as if it wasn't there, barely deflected at all. But some of them, a small fraction, bounced back. Not just deflected slightly, but bounced back at huge angles, sometimes almost straight back the way they'd come. Rutherford later said it was the most incredible thing that had ever happened to him in his life. He compared it to firing a 15-inch artillery shell at a piece of tissue paper and having the shell come back and hit you. Tissue paper doesn't bounce back artillery shells.
Something inside those gold atoms was far denser, far more concentrated, far more solid than the plum pudding model allowed for. What it meant, and Rutherford was quick to see it, was that the positive charge and nearly all the mass of the atom was concentrated in a tiny, incredibly dense core at the center. He called this core the nucleus. The electrons orbited far away from this nucleus, like planets around a sun. And between the nucleus and the electrons, there was essentially nothing. Empty space. Vast, proportionally speaking, amounts of empty space. And this is where I want you to really sit with the picture that Rutherford revealed, because it's one of the most extraordinary things in all of science, and it bears directly on our story about invisibility. The atom is almost entirely empty. If you could blow up the nucleus of a hydrogen atom to the size of a basketball, the single electron orbiting it would be roughly 2 miles away. Everything in between would be vacuum, nothing. And the nucleus itself, that basketball in this analogy, would contain nearly all the mass of the atom, nearly all the weight, packed into a space so small that it's literally invisible even to the most powerful optical microscopes ever built. Think about what that means for the everyday world around you. The pillow under your head, the walls of your room, your own body, all of it is made of atoms, and all of those atoms are almost entirely empty space. If you could somehow remove all the empty space from all the atoms in every human being on Earth, all 8 billion of us, the remaining matter would fit inside a sugar cube. One sugar cube, with the mass of all of humanity. That's how empty atoms are. And sitting there at the center of each atom, impossibly small, impossibly dense, invisible to every instrument available in 1911, was the nucleus. And Rutherford had just shown that this invisible speck was where the action was. All the mass, all the positive charge. And, though it would take a few more years to understand this fully, all the energy. Because the nucleus of an atom, particularly a heavy atom like uranium or radium, is held together by a force of extraordinary power. We call it the strong nuclear force. And it is by far the most powerful force in nature. It has to be, because the protons in a nucleus are all positively charged, and positive charges repel each other with great intensity. The only reason those protons don't fly apart is that the strong nuclear force, which operates only over incredibly short distances, the width of a nucleus itself, is powerful enough to overcome that repulsion and bind everything together. And here is the key insight, the one that makes the whole story of nuclear energy possible. The energy required to hold a nucleus together is enormous, unimaginably enormous compared to the energy involved in chemical reactions, the kind of reactions that happen when you burn coal or gasoline or wood. Chemical reactions involve the electrons, the outer parts of the atom, the parts that interact with other atoms to form molecules. Those interactions involve relatively small amounts of energy. When you burn a piece of wood, you're rearranging the electrons in carbon and oxygen atoms to form carbon dioxide.
and the energy released is enough to heat a room. When you split a nucleus, you're releasing a portion of the energy that was holding the nucleus itself together, and the amount of energy involved is roughly 1,000,000 times greater, atom for atom, than what you get from a chemical reaction. 1,000,000 times. That number is not hyperbole, not a metaphor. When a uranium atom splits, the energy released from that single atom is literally about 1,000,000 times more than the energy released when a carbon atom combines with oxygen. And this colossal disproportion between nuclear and chemical energy is the fundamental fact that makes nuclear power possible and nuclear weapons terrifying, and the whole nuclear age what it is. Rutherford's discovery of the nucleus didn't immediately lead to this understanding. It would take another 3 decades and the work of many more physicists before the full picture emerged. But Rutherford had found the vault. He had shown where the energy was hidden. And now the question was, could anyone figure out how to open it? The answer would come from an unexpected direction, from a quiet laboratory in Berlin, from 2 chemists who weren't entirely sure they believed their own results. And the year it happened, 1938, was a year when the world could least afford to discover a new source of unimaginable power. Through the 1920s and 30s, physicists made enormous progress in understanding the atom. The nucleus was mapped out in greater and greater detail. James Chadwick discovered the neutron in 1932, the electrically neutral particle that sits alongside protons in the nucleus. This was hugely important, because the neutron's lack of electrical charge meant it could approach and enter a nucleus without being repelled by the positive charge of the protons. Think of the nucleus as a fortress with electrified walls. A positively charged particle trying to get in would be pushed away by the electrical repulsion. But a neutron, being neutral, could walk right through the walls as if they weren't there. The neutron was the key that could open the lock. Enrico Fermi, a young Italian physicist working in Rome, seized on this idea. Starting in 1934, he began systematically bombarding every element he could find with neutrons to see what would happen. His team would place a neutron source, typically a small amount of radon mixed with beryllium, next to a sample of some element, and then use a Geiger counter to measure the radioactivity of the sample afterward. If the neutron had been absorbed by the nucleus, the atom would become a heavier isotope, often an unstable one that would be radioactive. Fermi worked his way through the periodic table, element by element, and when he got to uranium, the heaviest naturally occurring element, something peculiar happened. The results were confusing. He thought he had created new, heavier elements beyond uranium on the periodic table, elements that had never existed before. He called them transuranic elements and published his results. The scientific community was excited. Creating new elements was a big deal. But a German chemist named Ida Noddack published a brief note suggesting something much more radical. Maybe, she wrote, the uranium nucleus wasn't absorbing the neutron and becoming heavier at all. Maybe it was breaking apart, splitting into 2 lighter elements. Nobody paid much attention to her suggestion at the time. It seemed outlandish. The nucleus was held together by the strongest force in nature. The idea that a single neutron could cause it to split in 2 seemed almost absurd. And yet, that is exactly what was happening. The definitive proof came in December 1938 in a laboratory at the Kaiser Wilhelm Institute for Chemistry in Berlin. Otto Hahn and Fritz Strassmann were repeating Fermi's uranium bombardment experiments, but with much more careful chemical analysis. Hahn was a superb chemist, meticulous and precise. When he analyzed the products of neutron-bombarded uranium, he kept finding barium. Barium, an element with an atomic number of 56, roughly half the atomic number of uranium, which is 92.
This made no sense in the existing framework. You don't get barium from uranium by chipping a few particles off the edge. Barium is roughly half of uranium. The nucleus wasn't being chipped. It was being split in two. Hahn was so puzzled, so uneasy, that he wrote to his former colleague, Lise Meitner, who had been forced to flee Germany earlier that year because of her Jewish heritage. Meitner was spending a miserable Christmas in a small Swedish village called Kungälv, far from her laboratory, far from her work, far from everything she knew. She received Hahn's letter and immediately grasped the significance. Working with her nephew, Otto Frisch, a physicist who happened to be visiting her over the holidays, Meitner sketched out the physics of what must be happening. She used the liquid drop model of the nucleus, which imagined the nucleus as a droplet of incompressible fluid held together by surface tension. When a neutron was absorbed, it added energy to the droplet, making it wobble. If the wobble was strong enough, the droplet could stretch into an elongated shape, like a peanut. And at some point, the electrical repulsion between the protons in the two halves would overcome the surface tension holding it together, and the droplet would pinch in two. It was fission, a word Frisch borrowed from biology, where it described the splitting of a living cell. Nuclear fission. And Meitner did something else that was critically important. She calculated the energy that would be released. Using Einstein's famous equation, E equals mc squared, she estimated that each fission event would release roughly 200 million electron volts of energy. To put that in perspective, a typical chemical reaction releases a few electron volts. 200 million versus a few. That million-fold difference we talked about earlier, right there, calculated on the back of an envelope in a Swedish village at Christmas. 200 million electron volts doesn't sound like much when you say it. But remember, that's from a single atom. A single uranium atom splitting in two. And a chunk of uranium the size of a golf ball contains something like 10 to the 24th atoms. That's a 1 followed by 24 zeros. If you could split all of them, the energy released would be equivalent to burning roughly 20,000 tons of coal. From a golf ball, 20,000 tons of coal. From a piece of metal you could hold in your hand, and every bit of it invisible. No flame, no smoke, no light, except for the radiation that no human eye could detect. The most concentrated source of energy ever discovered by human beings, and you could hold it in your palm without knowing what you were holding. When Frisch returned to Copenhagen and told Niels Bohr about the discovery, Bohr reportedly slapped his forehead and exclaimed that they had all been so blind, that fission was so obvious in retrospect. Within weeks, labs around the world had confirmed the result, and almost immediately, a terrifying question arose. When a uranium nucleus splits, it releases not just energy, but also 2 or 3 free neutrons. Those neutrons are fast and uncharged, and if they encounter another uranium nucleus, they can cause it to split as well, releasing more neutrons, which can cause more fissions, which release more neutrons, in a rapidly multiplying cascade. A chain reaction. If the chain reaction could be sustained and controlled, you would have a source of energy unlike anything the world had ever seen. If the chain reaction could be made to happen all at once, in an uncontrolled burst, you would have a weapon of unimaginable destructive power. Both possibilities were obvious to every physicist who understood fission. And in January 1939, with Europe sliding toward war and Nazi Germany still in possession of some of the world's best nuclear physicists, both possibilities were absolutely terrifying. The invisible fire had been discovered. The question now was whether it could be lit, and if so, whether anyone could control it.
The discovery of fission hit the physics community like a shockwave. Within months, laboratories in the United States, Britain, France, Germany, and the Soviet Union were scrambling to understand the implications. Could a chain reaction actually be sustained? Could it be controlled? And could it be weaponized? The answers to all three questions would come from the same man, Enrico Fermi, the Italian physicist who had unknowingly been splitting uranium atoms in Rome for years without realizing what he was doing.
Fermi had left Italy in December 1938, just weeks before Hahn and Strassmann published their fission results. He had travelled to Stockholm to accept the Nobel Prize for his neutron bombardment work, and from there, instead of returning to Mussolini's Italy, he took his family directly to New York. His wife, Laura, was Jewish, and the racial laws that Mussolini's government had recently enacted made Italy no longer safe for her. Fermi arrived in the United States as a refugee, one of the most brilliant physicists alive, and he immediately took a position at Columbia University. When news of fission reached him in New York, Fermi understood the possibilities faster than almost anyone. He had the experimental experience, having spent years working with neutrons and uranium. He had the theoretical chops, being one of the very few physicists equally gifted in both theory and experiment. And he had, beneath his calm and methodical exterior, an enormous ambition. Fermi wanted to build the world's first nuclear reactor. He wanted to prove that a self-sustaining chain reaction was possible, and he wanted to do it before anyone else. But there was a problem, and it was a problem of visibility, or rather, the total lack of it. Nobody had ever seen a chain reaction. Nobody had ever observed, even indirectly, what would happen when fission neutrons were allowed to multiply freely in a large mass of uranium. Would the reaction sustain itself? Would it fizzle out? Would it accelerate out of control and blow up? The theoretical calculations suggested that a controlled chain reaction was possible under the right conditions, but the calculations depended on dozens of physical parameters that had never been precisely measured. The probability that a given neutron would cause a fission event, the average number of neutrons released per fission, the likelihood that a neutron would be absorbed by uranium-238 without causing fission, wasted, lost to the chain reaction, the degree to which various materials would absorb neutrons and slow the reaction down. All of these numbers had to be known, and known precisely, before you could design a reactor that would work. And every single one of them was invisible. You couldn't watch neutrons moving through uranium. You couldn't see fission happening. You couldn't observe the chain reaction directly. Everything had to be inferred from indirect measurements, counts on a Geiger counter, readings on an ionization chamber, deflections on an oscilloscope. The entire enterprise was, from start to finish, an exercise in trusting instruments to tell you what your senses never could. Fermi spent the next 3 years, from 1939 to 1942, doing something that was equal parts physics and engineering, and sheer, dogged persistence. He was building up the knowledge base, one painstaking measurement at a time, to determine whether a self-sustaining chain reaction was feasible and how to make it happen. The key insight was that natural uranium, the kind you dig out of the ground, contains 2 isotopes, uranium-238, which makes up about 99.3% of natural uranium, and uranium-235, which makes up only about 0.7%. Only uranium-235 is readily fissile, meaning it will split when hit by a slow neutron. Uranium-238, the dominant isotope, is more likely to simply absorb a neutron without splitting, capturing it and becoming uranium-239, which eventually decays into plutonium-239. That absorption by uranium-238 is wasteful from the chain reaction's perspective. Every neutron absorbed by 238 is a neutron that can't go on to split a 235 atom and keep the chain going. So Fermi had a problem.
He had natural uranium that was mostly the wrong isotope. Only a tiny fraction was the useful one. And yet, separating the two isotopes, enriching the uranium to increase the proportion of 235, was extraordinarily difficult and expensive. Nobody in 1940 had the technology to do it on a large scale. Fermi had to find a way to make a chain reaction work with natural uranium as it came out of the ground, with only that tiny 0.7% of 235 doing the actual fissioning. The solution was the moderator. Here's the physics, and it's beautifully counterintuitive. When a uranium-235 atom splits, the neutrons that come flying out are moving very fast. They're called fast neutrons, and they carry a lot of kinetic energy. The problem is that fast neutrons are not very efficient at causing more fissions in uranium-235. A fast neutron zipping past a uranium-235 nucleus is like a car doing 100 miles an hour past a gas station.
It goes by too quickly to stop. To maximize the chance that a neutron will cause fission in the next uranium-235 atom it encounters, you need to slow it down. A slow neutron, what physicists call a thermal neutron, is much more likely to be absorbed by a uranium-235 nucleus and trigger fission. A slow neutron is like a car rolling past the gas station at 5 miles an hour. It's much more likely to pull in. So how do you slow down neutrons? You put something in the way that the neutrons will bounce off of, losing energy with each bounce, the way a billiard ball loses energy when it bounces off the cushions. The ideal material for this is something with atoms roughly the same mass as a neutron, because energy transfer is most efficient when the colliding objects have similar masses. Hydrogen is perfect for this, and water, which is full of hydrogen, is an excellent moderator.
But water also absorbs neutrons, which means it steals some of them from the chain reaction. For natural uranium, which has so few fissile atoms to begin with, you can't afford to lose too many neutrons to absorption. Fermi chose graphite, pure carbon. It was a reasonably good moderator, slowing neutrons down effectively, and it absorbed far fewer neutrons than water. The key word here is pure, because even tiny amounts of impurities in the graphite, particularly boron, which is a voracious neutron absorber, could poison the whole reaction. Fermi needed graphite of extraordinary purity, purer than any that had ever been manufactured. Getting that graphite was a saga in itself. Fermi's team tested batch after batch from various manufacturers, measuring the neutron absorption of each sample. Most were too impure. Eventually, they found a supplier, the National Carbon Company, that could produce graphite clean enough to work. The company didn't fully understand why these physicists needed such pure graphite, and Fermi couldn't tell them, because by this time the work was classified as part of the broader effort to develop nuclear weapons. By 1942, Fermi had moved to the University of Chicago, where his project was now part of the Manhattan Project, the massive secret program to build an atomic bomb. Fermi's immediate task wasn't to build a bomb. His task was to prove that a self-sustaining chain reaction was possible, because without that proof, nobody could be sure that a bomb would work, and nobody could produce the plutonium that one of the bomb designs required. The reactor he built was called Chicago Pile 1, and calling it a pile was perfectly accurate because that's exactly what it was. It was a pile of graphite bricks with chunks of uranium embedded in them.
Layers of graphite. Then a layer of graphite with uranium. Then more plain graphite. Then more uranium. Stacked up like an enormous cubic wedding cake in a squash court beneath the west stands of the university's football stadium. Stag Field, it was called. The stadium was no longer used for football, and the space beneath the stands was available. It wasn't the safest or most sensible location for the world's first nuclear reactor,
being in the middle of a major city, but the war created urgencies that overrode normal caution. The pile was roughly 25 feet wide and 20 feet tall when completed. It contained roughly 40,000 slugs of uranium metal and about 19,000 blocks of uranium oxide, all embedded in approximately 400 tons of graphite. There was no radiation shielding, no containment structure, nothing that you would recognize from a modern nuclear power plant. If the reaction had gone out of control, there was no engineered system to stop it. The only safety measures were the control rods, strips of cadmium-coated wood that could be inserted into the pile to absorb neutrons and slow the reaction, and a single safety rod, nicknamed ZIP for Zone of Imminent Precipitation, that was attached to a rope. If something went wrong, a man standing on a platform above the pile would cut the rope with an axe, and the rod would fall into the pile under gravity, hopefully absorbing enough neutrons to shut the reaction down. There was also a suicide squad, a group of 3 men standing on top of the pile with buckets of cadmium sulfate solution, a powerful neutron absorber. If the control rods failed and the zip rod failed, their job was to pour the solution over the pile by hand. Nobody talked much about what would happen to them afterward. On December 2nd, 1942, Fermi directed the experiment. The control rods were withdrawn, inch by inch, and the neutron count was monitored using instruments, boron trifluoride counters that clicked faster as the neutron flux increased. There was nothing to see. No fire, no glow, no dramatic visual display of any kind. Just the clicking of counters and the scratching of a pen on a chart recorder, drawing a line that crept slowly upward. Fermi had calculated, with characteristic precision, exactly how far each control rod needed to be withdrawn to reach criticality, the point where the chain reaction would become self-sustaining. As the rods came out, the neutron count rose. Each time a rod was withdrawn, the count would spike upward, then level off. Not yet self-sustaining. The reaction was still subcritical, meaning each generation of neutrons was slightly smaller than the one before it. The fire was almost lit, but not quite. At 2:25 in the afternoon, Fermi ordered the final control rod withdrawn another foot. The neutron count began to rise, and this time it didn't level off. The pen on the chart recorder drew a line that curved upward, steadily, smoothly, with that characteristic exponential shape that meant the chain reaction was sustaining itself. Each generation of neutrons was producing slightly more than one neutron to continue the chain. The reaction was supercritical. Fermi watched the instruments for several minutes, his expression calm and focused. He verified the readings. He compared them to his calculations. At 3:25, exactly 1 hour after achieving criticality, he ordered the control rods reinserted and the reaction shut down. Eugene Wigner, the Hungarian-American physicist who was present, produced a bottle of Chianti that he had been saving for the occasion. They drank from paper cups in the cold squash court, a muted celebration. Arthur Compton, the physicist who was overseeing the project, made a cryptic phone call to James Conant at Harvard. "The Italian navigator has just landed in the New World," he said. "How are the natives?" Conant asked. "Very friendly," Compton replied. And that was it. The world's first controlled, self-sustaining nuclear chain reaction, the first time the invisible fire had been deliberately lit and deliberately managed. No explosion, no drama, no spectacle of any kind. Just a line on a chart recorder, rising and then falling, witnessed by a few dozen people in a squash court in Chicago on a cold December afternoon. Think about what an extraordinary moment that was,
and how invisible it was. No one outside that squash court knew it had happened. No one could have detected it with their senses. If you had walked past Stag Field that afternoon, you would have seen nothing unusual, heard nothing, felt nothing. The most significant scientific achievement since the discovery of fire itself, and it was utterly, completely, silently invisible. But Fermi had proven the crucial point. A chain reaction could be sustained. A chain reaction could be controlled. Nuclear energy was real, and it could be managed. The invisible fire could be lit, and it could be put out. What Fermi had not proven, and what nobody would prove for another decade, was that this invisible fire could do useful work. Chicago Pile 1 initially produced just half a watt of thermal energy, barely enough to light a Christmas tree bulb. Fermi carefully ramped it up to about 200 watts before ordering the control rods reinserted. The gap between half a watt and a functioning power plant was enormous, and bridging it would require not just better physics, but entirely new engineering. Because controlling an invisible fire that produces half a watt is one thing, controlling an invisible fire that produces 1 billion watts is something else entirely. And the question of how to do that, how to build a machine that could safely harness the invisible fire at enormous scale, is the story of the nuclear reactor. A machine unlike any other in human history. A machine that runs on a fuel that doesn't burn, produces energy through a process that cannot be seen, and must be monitored and controlled entirely through instruments, because every important thing happening inside it is invisible to the human beings who operate it. But before we open that machine up and look inside, we need to understand how it got here, because the nuclear reactor wasn't invented for electricity, it was invented for war. And the story of how a military technology became a civilian power source involves one of the most driven, most difficult, and most consequential people in the history of engineering. There is a strange and uncomfortable truth at the heart of nuclear energy, and it's this. The technology that powers your local hospital tonight was born inside a weapons program. The first reactors were not built to generate electricity, they were built to produce plutonium for atomic bombs. Chicago Pile 1 was not a power plant, it was a proof of concept for the production of weapons material. The massive reactors that followed it at Hanford, in the desert of Washington state, were industrial-scale plutonium factories. They produced the plutonium that went into the Fat Man bomb, the one that destroyed Nagasaki on August 9, 1945. The invisible fire was first lit not to illuminate, but to destroy. And the transition from weapon to furnace, from military to civilian, was neither smooth nor inevitable. It happened because of specific people making specific decisions under specific pressures. And the most important of those people was a man named Hyman Rickover.
Rickover was a captain in the United States Navy and later an admiral. And he was one of the most difficult, demanding, and consequential figures in the history of technology. He was small, wiry, sharp-tongued, and utterly relentless. He drove his subordinates mercilessly and alienated his superiors regularly. He was passed over for promotion multiple times, and each time he fought his way back. He was, by all accounts, extraordinarily unpleasant to work for, and he transformed the world. Rickover's vision was simple and audacious. He wanted to put a nuclear reactor inside a submarine. The advantage was obvious. A conventional submarine of the late 1940s ran on diesel engines on the surface and battery power when submerged. The batteries had limited capacity, which meant the submarine could only stay submerged for a day or two before it had to surface and recharge. A nuclear-powered submarine would never need to surface for fuel. It could stay submerged for months. It could travel at full speed underwater for as long as the food supply lasted. It would be a true submarine, a ship of the deep, rather than a surface ship that could temporarily dive. But building a reactor small enough and reliable enough and safe enough to operate inside a submarine, crewed by young sailors with no physics degrees, in a sealed metal tube deep underwater, where a malfunction could mean the death of everyone aboard. That was a challenge of the first order. Rickover attacked it with characteristic ferocity. He assembled a team of the best naval engineers he could find and worked them around the clock. He insisted on standards of quality and reliability that were far beyond anything the nuclear program had previously required. Every component was tested and retested. Every weld was inspected and re-inspected. Every procedure was written, reviewed, practiced, and critiqued.
Rickover personally interviewed every officer who would serve on a nuclear submarine, and his interviews were legendary for their intensity, their unpredictability, and their occasional cruelty. He was looking for people who would take the responsibility of managing an invisible fire inside a sealed tube underwater as seriously as it deserved to be taken. And if he didn't think you measured up, he told you so in terms that left no room for misunderstanding. The result was the USS Nautilus, which went to sea in January 1955. Its reactor was a pressurized water reactor, the same basic design that had been developed at Argonne National Laboratory in Illinois and tested in a prototype facility in Idaho. The reactor heated pressurized water. The hot water passed through a heat exchanger to produce steam. The steam drove a turbine, and the turbine drove the propeller. The entire nuclear propulsion plant fit inside the submarine's hull, and it worked. The Nautilus was a sensation. In 1958, it made the first submerged transit of the North Pole, traveling under the Arctic ice cap from the Pacific to the Atlantic. The voyage was a technical triumph and a public relations coup. And it proved that nuclear propulsion was not just feasible, but transformative. And here is where the transition from military to civilian happened. Rickover's pressurized water reactor, designed for submarines, became the template for the first civilian nuclear power plants. The reactor at Shippingport, Pennsylvania, which began generating electricity in 1957 and is generally considered the first commercial nuclear power plant in the United States, was essentially a scaled-up version of the submarine reactor. Rickover himself oversaw its construction.
The choice of the PWR as the basis for civilian nuclear power was driven not by any comprehensive analysis of which reactor design was best suited for electricity generation, but by the fact that the PWR was proven, that the engineering infrastructure existed to build it, and that Rickover's organization had the expertise and the drive to make it happen. Other reactor types, some of which might have been better suited for civilian power production, were set aside. The molten salt reactor, which we mentioned earlier, was one of these. The thorium fuel cycle, which could have reduced proliferation concerns and waste problems, was another. The history of nuclear energy is, in some ways, a history of paths not taken, of choices made under the pressure of time and circumstance that locked in a particular technological trajectory for decades to come. But whatever its origins, the civilian nuclear industry grew rapidly through the 1960s and 70s.
In the United States, France, Japan, the Soviet Union, and elsewhere, dozens of reactors were ordered and built. France, in particular, made a strategic decision to embrace nuclear power after the oil crisis of 1973, and today roughly 70% of France's electricity comes from nuclear reactors. The French nuclear program is often cited as the most successful example of a national energy transition, demonstrating that it is possible to build a large-scale, reliable, low-carbon electricity system based on nuclear energy in a relatively short period of time. And all of this, every reactor, every turbine, every megawatt of electricity, every day of operation, rests on the same fundamental bargain: trust the invisible. Trust that the chain reaction is under control, even though you can't see it. Trust that the barriers are holding, even though you can't feel the radiation they're blocking. Trust that the fuel is intact, even though you can't look at it. Trust the instruments. Trust the engineering. Trust the people. It is a remarkable thing when you think about it. a civilization powered in part by a fire no one can see, managed by people reading instruments that translate the invisible into numbers, contained by barriers designed to hold for decades against forces that no human sense can detect. It is an act of collective trust so profound that most people never think about it at all. They flip a switch, the light comes on, and they never wonder where the energy came from, or what invisible processes were required to deliver it, or how many people are working right now, tonight, to keep the invisible fire burning safely. But what does that actually mean in practice? How does the reactor that Rickover put inside a submarine, the reactor that became the template for nearly every nuclear power plant in the world, actually work?
What's happening inside that steel vessel, behind those concrete walls, in the invisible space where the fire burns? Let's slow down and walk through it, piece by piece, because this is the heart of the whole story. And I want to approach it from our particular angle, the angle of invisibility, because when you build a machine around a process that cannot be seen, every design decision is shaped by that fundamental constraint. Let's start with the fuel. In a coal-fired power plant, the fuel is coal. You can see it, touch it, shovel it, weigh it. You know when it's burning because it glows and gives off smoke. You know how much you have because you can look at the pile. You know when it's used up because it turns to ash. Everything about coal as a fuel is tangible and visible. Nuclear fuel is nothing like this. The fuel in most commercial nuclear reactors is uranium dioxide, a ceramic material that looks like a dark grey or black powder.
It's pressed into small cylindrical pellets, each about the size of a pencil eraser, maybe about half an inch tall and half an inch across. Each of those little pellets contains as much energy as roughly 1 ton of coal. 1 pellet, 1 ton. The energy density is almost beyond comprehension, and it's entirely invisible. You could hold one of those pellets in your hand and you would feel nothing. No heat, no vibration, no indication whatsoever of the staggering quantity of energy locked inside it. It would feel like a small, heavy, unremarkable piece of ceramic. These pellets are stacked end to end inside long, thin tubes made of a zirconium alloy, each tube roughly 12 to 14 feet long and less than half an inch in diameter. The zirconium is chosen carefully because it's strong, it resists corrosion, and most importantly, it's nearly transparent to neutrons. It doesn't absorb them. Neutrons pass through zirconium the way light passes through glass.
These filled tubes are called fuel rods, and they are bundled together, typically in square arrays of roughly 17 by 17 rods, to form what's called a fuel assembly. A single fuel assembly might contain over 260 individual fuel rods, and a typical large reactor core might contain roughly 200 fuel assemblies, for a total of around 50,000 individual fuel rods, each one loaded with those little ceramic pellets, each pellet containing the energy equivalent of a ton of coal. The entire reactor core, all 50,000 fuel rods, fits inside a steel vessel roughly 40 feet tall and maybe 15 feet in diameter. The vessel is made of carbon steel, with walls about 8 inches thick, lined on the inside with stainless steel to resist corrosion. This is the reactor pressure vessel, and it is one of the most carefully manufactured pieces of equipment in the world.
Every weld is inspected multiple times. Every section of steel is tested for microscopic flaws. Because this vessel is the primary barrier between the nuclear reaction and the outside world, and it must hold up under enormous pressure and intense radiation for decades without failure. Now, here's where the invisibility really matters. Inside that vessel, when the reactor is operating, the fuel is undergoing fission. Uranium-235 atoms are splitting, releasing energy and neutrons, and the neutrons are causing more atoms to split, sustaining the chain reaction. But you cannot see any of this. If you could somehow look inside the reactor vessel while it was operating, which you absolutely cannot do because the radiation would kill you in minutes, you would see nothing dramatic. No fire, no glowing fuel, no visible reaction. The fuel rods would look exactly as they looked before the reaction started. Metallic tubes standing in neat rows, submerged in water.
The only indication that anything was happening would be that the water was getting very hot. And that's the trick. That's the whole trick of a nuclear power plant. You take the invisible energy released by fission and you use it to heat water. Everything else, the turbines, the generators, the transformers, the transmission lines, everything from the water onward is essentially identical to a conventional power plant. The only difference is the heat source. In a coal plant, you burn coal to heat water. In a gas plant, you burn natural gas to heat water. In a nuclear plant, you split atoms to heat water. The water boils, turns to steam, the steam spins a turbine, the turbine drives a generator, the generator produces electricity. The nuclear part of a nuclear power plant is, in a very real sense, just an extraordinarily powerful and extraordinarily invisible furnace.
But the details of how that invisible furnace works, the engineering required to keep it running safely, are where the real complexity lives. Let me walk you through the two most common types of reactors in the world, because they handle the invisible fire in slightly different ways. The first type is called a pressurized water reactor, or PWR. Roughly 2/3 of the world's nuclear reactors are this type. The idea behind a PWR is to keep the water that flows directly through the reactor core under such high pressure that it cannot boil, even at temperatures well above water's normal boiling point. The water in the primary loop of a PWR can reach temperatures around over 600 degrees Fahrenheit. But because it's pressurized to roughly 155 times atmospheric pressure, it stays liquid. This superheated, highly pressurized water flows out of the reactor vessel and through a device called a steam generator, which is essentially a giant heat exchanger. Inside the steam generator, the hot primary water flows through thousands of thin metal tubes. And on the other side of those tubes is a separate supply of water at lower pressure. That secondary water absorbs the heat through the tube walls and boils, turning to steam. The steam then goes to the turbine. The crucial thing to notice here is that the water that actually touches the fuel rods, the primary water, never reaches the turbine. It circulates in a closed loop: reactor core, steam generator, and back. The water that goes to the turbine is the secondary water, which has been heated through the walls of the steam generator tubes, but has never been inside the reactor itself. This means the turbine, and everything downstream of it, never comes in contact with radioactive water. The primary loop, which is radioactive, is entirely contained within the reactor building. The secondary loop, which is clean, drives the turbine and condenser outside.
This two-loop design is a direct response to the invisibility problem. Because you can't see whether the primary water is contaminated with radioactive fission products, you keep it sealed away in its own loop, never letting it mix with the water that goes to the rest of the plant. The boundary between the two loops, the wall of those steam generator tubes, is a physical barrier between the radioactive and the non-radioactive worlds. It's the engineering embodiment of the principle: keep the invisible stuff contained. The second type is called a boiling water reactor, or BWR. In a BWR, there's only one loop. The water that flows through the reactor core is allowed to boil inside the reactor vessel itself, and that steam goes directly to the turbine. This is simpler in some ways because you don't need a separate steam generator, but it also means that the steam going through the turbine has been in direct contact with the fuel rods and is slightly radioactive.
The turbine hall in a BWR, therefore, has to be treated as a radiation area, with restricted access and additional monitoring. In a PWR, the turbine hall is essentially clean. Both designs use the same fundamental approach. Use fission to heat water. Use the hot water or steam to spin a turbine. Use the turbine to generate electricity. Both designs are surrounded by multiple layers of containment. Both designs rely on instruments, not human senses, to monitor what's happening inside the reactor. And both designs face the same fundamental challenge. How do you control something you can't see? The answer is control rods. Control rods are bars made of materials that are extremely good at absorbing neutrons. Cadmium, boron, hafnium, or silver-indium-cadmium alloys. When a control rod is inserted into the reactor core, it absorbs neutrons and slows down the chain reaction. When it's withdrawn, more neutrons are available to cause fission, and the reaction speeds up. By adjusting the position of the control rods, operators can increase or decrease the power output of the reactor. Think of it this way. The chain reaction depends on neutrons. If you remove neutrons from the system by absorbing them in control rods, the reaction slows down. If you let more neutrons participate by pulling the control rods out, the reaction speeds up. The control rods are the gas pedal and the brake, all in one. And they work in real time, meaning you can adjust them continuously to keep the reactor at exactly the power level you want. But here's what's remarkable about this system. The operators who adjust the control rods cannot see the neutrons they're controlling. They can't see the fission reactions they're speeding up or slowing down. They can't feel the change in the reactor's power output until it shows up on their instruments. They are managing an invisible process through indirect measurement, the way a pilot in dense fog flies entirely on instruments, trusting the dials and readouts to tell them what their eyes cannot. And this brings us to something important about reactor design, something that makes nuclear reactors fundamentally different from other energy systems and much safer than most people realize. It's a concept called negative feedback, and it is the unsung hero of nuclear safety. In most commercial reactor designs, the physics of the reactor itself works to limit the chain reaction. If the reactor starts getting too hot, the reaction naturally slows down. This happens for several reasons. First, as the fuel heats up, the uranium atoms move faster, vibrating more energetically, and this changes the way they interact with neutrons in a way that reduces the probability of fission.
This is called the Doppler effect, or Doppler broadening. And it's an immediate, automatic, physics-based brake on the reaction. You don't need an operator to do anything. You don't need a control system to kick in. The physics does it by itself. Second, in water-moderated reactors like PWRs and BWRs, as the water heats up, it becomes less dense. Less dense water is a less effective moderator, which means neutrons are not slowed down as efficiently, which means they are less likely to cause fission, which means the reaction slows down. And if the water actually boils and turns to steam, steam is a terrible moderator compared to liquid water, so the reaction slows down even more. In a PWR, if you somehow lost all the water in the reactor, the chain reaction would stop entirely, because there would be no moderator to slow the neutrons down to the speeds where they cause fission efficiently. Let me say that again, because it's counterintuitive and important. In a standard pressurized water reactor, if you remove all the water, the chain reaction stops. The water is both the coolant and the moderator. Without it, the neutrons are too fast to sustain the chain reaction. The reactor shuts itself down. The fire goes out.
Of course, this doesn't mean everything is fine, because even after the chain reaction stops, the fuel still produces heat from the decay of fission products, what's called decay heat. And that heat has to be removed, or the fuel will eventually overheat and be damaged. Managing decay heat after shutdown is one of the great challenges of nuclear safety, and we'll come back to that. But the chain reaction itself, in a well-designed reactor, has multiple built-in mechanisms to shut itself down if things go wrong. This is the engineering genius of the modern nuclear reactor. The invisible fire is not just controlled by human operators, it is controlled by physics.
The same laws of nature that make fission possible also make uncontrolled fission very difficult to sustain, at least in a properly designed reactor. The fire tends to tamp itself down. It resists getting out of control. The operators are there to fine-tune and optimize, but the fundamental safety of the system is built into the physics. And yet, the invisibility remains. All of these elegant, self-regulating mechanisms are invisible. The Doppler broadening is invisible. The change in moderator density is invisible. The negative feedback coefficient is a number on a piece of paper. The reactor operator cannot see any of these things happening. They can only see the instruments that measure the consequences: temperature readings, pressure gauges, neutron flux monitors, coolant flow rates. They are managing an invisible fire through the lens of instruments, trusting numbers on screens to tell them that the physics is doing what it's supposed to do.
And this dependence on instruments, this absolute necessity of building eyes where evolution gave us none, is what makes the next part of our story so crucial. Because the entire safety case for nuclear energy depends on our ability to see the invisible. And building that ability turned out to be one of the most extraordinary feats of engineering in human history. Let me go a little deeper into the physics here, because there are a few more things happening inside the reactor that are important for understanding how the invisible fire behaves, and each of them is beautifully counterintuitive. First, there's the question of delayed neutrons. When a uranium-235 atom splits, most of the neutrons are released instantly, within a trillionth of a second of the fission event. These are called prompt neutrons, and they make up about 99.35% of all fission neutrons.
If the chain reaction depended entirely on prompt neutrons, it would be essentially uncontrollable, because the time between one generation of fissions and the next would be measured in microseconds, far too fast for any human operator or mechanical control system to respond to. But a small fraction of the neutrons, about 0.65%, are not released instantly. They come from the radioactive decay of certain fission products, and they emerge seconds or even minutes after the original fission event. These are called delayed neutrons, and although they represent less than 1% of the total, they completely change the dynamics of the reactor. Because of the delayed neutrons, the effective time between generations of the chain reaction is stretched from microseconds to seconds. And seconds is a timescale that operators and control systems can work with.
This is a profound piece of luck. And I use the word luck deliberately, because the fraction of delayed neutrons is determined by the fundamental physics of fission and nuclear decay. It could have been different. If the delayed neutron fraction was smaller, reactors would be much harder to control. If it was zero, controlled chain reactions might be effectively impossible with any conceivable technology. The fact that roughly 0.65% of fission neutrons happen to be delayed by enough time to make reactors controllable is one of those happy accidents of nuclear physics that made the entire enterprise of nuclear energy feasible. Reactor operators keep the reactor in a state where the chain reaction is sustained by the combination of prompt and delayed neutrons. In this state, called delayed critical, the reactor responds slowly and predictably to changes in the control rod positions.
If the reactor were to go prompt critical, meaning the chain reaction could sustain itself on prompt neutrons alone, the power would increase extremely rapidly, far faster than any control system could respond. This is, in essence, what happened at Chernobyl. The reactor went prompt critical, and the power surged by a factor of hundreds in a fraction of a second. The second thing worth understanding is xenon poisoning, which is one of the most peculiar challenges of reactor operation. Xenon-135 is a fission product produced indirectly through the decay chain of iodine-135, and it is an astonishingly effective neutron absorber. Xenon-135 has a neutron absorption cross-section roughly 2.6 million barns, where a barn is a unit of area used to describe the probability of a nuclear interaction. For comparison, the fission cross-section of uranium-235 for thermal neutrons is about 585 barns. Xenon-135 is roughly 4,500 times more effective at absorbing neutrons than uranium-235 is at being split by them. What this means in practice is that Xenon-135, which builds up in the fuel during operation, acts as a powerful brake on the chain reaction. At steady state, the xenon is being produced and destroyed at equal rates, and operators compensate for its presence by adjusting the control rods. But when the reactor power is changed, the xenon concentration doesn't change instantly. It lags behind, producing transient effects that can persist for hours. The most dramatic example of this is the xenon pit, or xenon dead time. After a reactor is shut down or reduced to very low power, the xenon-135 concentration actually increases for several hours because the iodine-135 that was built up during operation continues to decay into xenon-135. But the xenon is no longer being destroyed by neutron absorption because the neutron flux has dropped. The result is a buildup of xenon that can be so intense that it is temporarily impossible to restart the reactor, even with all the control rods fully withdrawn. The reactor is, in effect, poisoned by its own fission products. Operators must wait for the xenon to decay away, which takes roughly a day before they can restart. This was one of the factors in the Chernobyl accident. The operators, having brought the reactor to low power, encountered the xenon buildup and tried to override it by withdrawing the control rods further than safety procedures allowed. They were fighting against an invisible poison, a fission product they couldn't see or detect directly, that was choking the chain reaction. Their response, pulling out too many control rods, left the reactor in a dangerously unstable configuration with insufficient shutdown margin. When they then tried to increase power for their test, the combination of the positive void coefficient and the insufficient control rod margin proved catastrophic. The third thing worth mentioning is burnup, the measure of how much energy has been extracted from a given amount of fuel. As the fuel operates in the reactor, the fissile uranium-235 is consumed, and fission products accumulate. Some of these fission products are neutron absorbers, like xenon, that reduce the reactivity of the fuel. Others are gaseous, like krypton and xenon, and they build up pressure inside the fuel rods. Still others cause the fuel pellets to swell, potentially putting stress on the cladding. Managing burnup is a complex art. Reactor operators want to extract as much energy as possible from each fuel assembly before replacing it, because fresh fuel is expensive and the refueling process requires shutting down the reactor for several weeks. But pushing burnup too high can compromise the integrity of the fuel cladding, increase the risk of fuel failure, and produce higher concentrations of problematic fission products. The optimization of fuel burnup involves balancing economic efficiency against safety margins, and it requires detailed computer simulations of the isotopic changes happening inside each fuel pellet. Changes that are entirely invisible and can only be inferred from indirect measurements and theoretical calculations.
All of this, the delayed neutrons, the xenon transients, the burn-up management, is happening silently inside the reactor core, governed by the laws of physics, monitored by instruments, and managed by operators who must build a mental model of processes they will never directly observe. The invisible fire is not just invisible, it is complex, dynamic, and constantly changing, even when the reactor appears to be running at a perfectly steady state. The needles on the instruments may look stable, but beneath that stability, trillions of atoms are splitting every second. Xenon is building up and being destroyed. Fuel is slowly changing its composition. Neutrons are being born and absorbed and scattered in a ceaseless, invisible storm. And the operators watch the numbers and trust the physics and adjust the rods and keep the fire burning at exactly the right level, hour after hour, day after day, invisible and extraordinary and completely ordinary, all at once. And the only reason any of it works, the only reason operators can manage a process they cannot see, hear, or feel, is that someone, over the past century, built the instruments that make the invisible legible. The story of those instruments, the artificial eyes and ears and nerves that translate the invisible fire into numbers a human being can act on, is a story of ingenuity that doesn't get nearly enough credit. Imagine you had to manage a furnace, a very large and very powerful furnace, with the following constraints. You cannot see the fire. You cannot feel its heat through the walls. You cannot smell any combustion products. You cannot hear the flames. The furnace is sealed inside a container with walls so thick that no sensory information of any kind reaches you. And yet you must keep the fire burning at exactly the right level, not too hot, not too cool, adjusting constantly to match the demand for power. If you let it get too hot, the furnace could be damaged. If you let it get too cool, it might go out, and relighting it is a slow and complex procedure. That is, in essence, the challenge of operating a nuclear reactor. And to meet that challenge, engineers have built one of the most sophisticated instrumentation systems ever devised. Let's walk through the sensors that give operators their eyes. The most fundamental measurement in a nuclear reactor is neutron flux, the number and intensity of neutrons flowing through the reactor core at any given moment. Neutron flux is the heartbeat of the reactor. It tells you how fast the chain reaction is running. If the flux is rising, the reaction is speeding up. If it's falling, the reaction is slowing down. If it's stable, the reaction is at equilibrium, producing exactly the same number of neutrons in each generation as it uses up. Measuring neutrons is not straightforward, because neutrons are, as we've discussed, completely invisible. They have no electrical charge, so they don't interact with electric or magnetic fields. They don't produce light. They don't create sound. The only way to detect a neutron is to let it interact with a material that converts the neutron's invisible presence into something measurable. The most common approach uses a gas-filled chamber containing a material with a high probability of absorbing neutrons, typically boron-10 or helium-3. When a neutron enters the chamber and is absorbed by one of these atoms, the resulting nuclear reaction produces charged particles, and those charged particles ionize the gas, creating a tiny electrical pulse that can be counted. Each pulse represents one neutron detected. Count the pulses per second, and you have a measure of the neutron flux. At very low power levels, during startup, you can actually count individual neutrons. One click,
2 clicks, 3 clicks.
Like a Geiger counter, each click representing one neutron entering the detector and being absorbed. The clicking speeds up as the reactor approaches criticality, faster and faster, until the clicks merge into a continuous roar and the instrument switches from counting individual pulses to measuring the overall current, a smooth signal proportional to the neutron flux. At full power, a large reactor might have a neutron flux of something like 10 to the 13th neutrons per square inch per second. That number is almost impossible to visualize. Trillions of invisible particles passing through every square inch of the reactor core every second, each one capable of splitting another atom and releasing more energy and more neutrons. And the only reason we know they're there is a signal on a wire. But neutron flux alone isn't enough. Operators also need to know the temperature of the fuel, the temperature and pressure of the coolant water, the flow rate of the coolant, the water level in the reactor vessel, the radiation levels in various parts of the plant, the concentration of fission products in the coolant, and dozens of other parameters, all of them measured by instruments, all of them invisible to the naked eye. Temperature is measured by thermocouples, devices that produce a tiny voltage proportional to temperature. These are embedded throughout the reactor system, in the coolant at the inlet and outlet of the core, in the primary piping, in the steam generators, in the containment building itself. Each thermocouple is a tiny point of visibility in an otherwise invisible system, translating heat into an electrical signal that can be displayed on a screen in the control room. Pressure is measured by transducers that convert mechanical pressure into an electrical signal.
Coolant flow rate is measured by differential pressure across calibrated restrictions in the piping, or by ultrasonic flow meters that measure the speed of sound through the moving water. Radiation levels are measured by a network of detectors placed throughout the plant, in the containment building, in the turbine hall, at the site boundary, in the exhaust stacks, in the liquid waste systems. Each detector is another eye, watching for the invisible. The control room of a nuclear power plant is, in a very real sense, a room full of artificial senses. Hundreds of instruments, each measuring one aspect of the invisible process happening inside the reactor, each converting some imperceptible physical quantity into a number on a screen, or a position of a needle, or a color on a display. Operators are trained for years, not just in the physics of fission and the engineering of the plant, but in the art of reading these instruments, of building a mental picture of what the reactor is doing based entirely on indirect evidence. They learn to recognize patterns in the data, to spot anomalies, to understand what a rising temperature in one area, combined with a falling pressure in another area, means for the overall state of the plant. They develop, through training and experience, an intuition for the invisible. And this is, when you think about it, one of the most remarkable cognitive achievements in human history. Our brains evolved to navigate a world of visible, tangible, audible stimuli. We see a predator and we run. We smell smoke and we look for fire. We hear thunder and we seek shelter. But a nuclear plant operator must construct an entire mental model of a complex, dangerous, invisible process from nothing but numbers on screens. They must, in a sense, learn to see without eyes. They must train their brains to interpret abstract data with the same immediacy and confidence that their ancestors brought to interpreting the rustle of grass or the crack of a branch. This training takes time. In the United States, a reactor operator must complete a multi-year training program that includes classroom instruction, simulator training, and on-the-job experience before being licensed by the Nuclear Regulatory Commission. The simulator is a full-scale replica of the plant's control room, connected not to a real reactor, but to a computer model that behaves exactly like the real thing. Operators spend hundreds of hours in the simulator, practicing normal operations and, critically, practicing emergency responses. What to do if a coolant pump fails? What to do if a steam line breaks? What to do if multiple systems fail simultaneously? They practice until the correct responses become automatic, until reading the instruments and interpreting their meaning becomes as natural as reading a facial expression. And even with all this training, even with all these instruments, there are limits to what technology can make visible. Some things remain stubbornly, dangerously invisible. Radiation damage to materials, for example, the intense neutron bombardment inside a reactor core, gradually changes the physical properties of the metals it hits. Steel becomes more brittle. Welds develop microscopic cracks. Concrete degrades. These changes are invisible from the outside and can only be detected through periodic inspections. Ultrasonic testing, X-ray inspection, physical sampling of materials. The reactor must be shut down for these inspections, and the process is painstaking. Because any flaw that escapes detection could become a pathway for the invisible to escape its containment. Corrosion is another invisible threat. The water inside a nuclear reactor is carefully controlled for chemistry, kept at precise levels of acidity and dissolved oxygen, because even small deviations can accelerate corrosion of the zirconium fuel cladding or the steel piping. Corrosion happens at the atomic level, invisibly, gradually, and it can thin the walls of pipes and tubes until they fail under pressure. Monitoring water chemistry is a constant, never-ending task, a continuous battle against an invisible enemy that is always there, always working, always trying to eat through the barriers that keep the invisible fire contained. But there is one moment, one extraordinary moment, when the invisible fire briefly, beautifully, reveals itself. And if you've never heard of it, it might be one of the most haunting images in all of science. Deep inside a nuclear reactor, when the core is operating at power, something happens that you would never notice through the thick steel walls and concrete shielding.
But if you could look into the water surrounding the fuel rods, if you could somehow peer inside the reactor vessel with your own eyes, you would see something strange and beautiful. A faint blue light. Not the blue of a gas flame or the blue of a clear sky. A different kind of blue, deeper, more ethereal, more unsettling. It seems to come from everywhere and nowhere, a gentle, otherworldly luminescence suffusing the water itself. It shifts and shimmers like something alive. This is Cherenkov radiation, and it is the only moment in the entire nuclear process when the invisible fire becomes visible. Here's what's happening. When certain particles produced by fission, particularly fast electrons from beta decay, travel through water at a speed greater than the speed of light in that medium, they produce a cone of electromagnetic radiation, similar to the sonic boom produced by an airplane exceeding the speed of sound. Light travels slower in water than in vacuum, roughly 75% as fast. So a sufficiently energetic particle can actually outrace the light in water, even though nothing can exceed the speed of light in vacuum, which is an absolute cosmic speed limit. That cone of electromagnetic radiation manifests as blue ultraviolet light. Cherenkov radiation. Named after Pavel Cherenkov, the Soviet physicist who first described the phenomenon in 1934, work for which he shared the Nobel Prize in 1958. You can see Cherenkov radiation most easily, not in operating reactors, where the core is sealed and shielded, but in research reactors with open pools, and in the storage pools where spent fuel assemblies are kept after being removed from the reactor. Spent fuel pools are large, deep pools of clear water, typically 40 feet deep or more, where used fuel assemblies are stored while their most intense, short-lived radioactivity decays.
If you stand at the edge of a spent fuel pool and look down into the water, you can see the fuel assemblies arranged on the bottom and surrounding them, particularly around the most recently discharged fuel, that faint, extraordinary blue glow. It is, by all accounts, one of the most beautiful things you will ever see. Visitors to nuclear facilities who have been allowed to view spent fuel pools often describe the experience as almost hypnotic. The blue light has a purity and an intensity that is unlike anything produced by conventional means. It is light created not by heat, not by chemistry, not by electricity, but by particles moving faster than light itself can travel through water. It is, in a sense, the visible edge of the invisible fire. And there is something deeply poetic about the fact that this one visible manifestation of nuclear energy is also deeply alien. Cherenkov radiation looks like nothing else in the natural world.
It doesn't resemble firelight or sunlight or starlight or any other light that human beings evolved to recognize. It is a light from outside our experience, a light that signals the presence of energies and processes that our senses were never built to detect. It is beautiful, but it is also a reminder that the invisible fire is something genuinely new in the world, something that human beings have only recently learned to handle, and something that demands a kind of respect and caution that is different from anything we've needed before. Because when the invisible fire escapes its containment, when the barriers fail and the instruments go blind and the invisible becomes uncontrolled, the consequences can be devastating. Not because nuclear energy is uniquely dangerous in terms of the number of people it harms, because statistically, it kills far fewer people per unit of energy than coal or oil or even natural gas, but because the nature of the harm is invisible, insidious, and lingering in ways that tap into our deepest fears about threats we cannot perceive. And the story of what happens when the invisible fire escapes is the story we need to tell next. In the entire history of commercial nuclear power, stretching back over 70 years and encompassing roughly 18,000 reactor years of operation across more than 30 countries, there have been three major accidents that most people know about. 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima Daiichi in 2011. Each of these accidents taught the nuclear industry profound lessons. Each one exposed a different kind of failure, a different way in which the invisible fire could slip past the barriers designed to contain it. And each one reshaped the way the world thinks about nuclear safety. Let's walk through them, one by one, because the details matter. The details always matter with nuclear energy, because the devil is always invisible. 3 Mile Island, March 28, 1979. 3 Mile Island is a nuclear power station in Pennsylvania, on an island in the Susquehanna River. Unit 2, the reactor involved in the accident, was a pressurized water reactor that had been operating for only about 3 months. The accident began with a relatively minor malfunction. A valve in the secondary cooling system, the non-nuclear side, stuck open. This caused a pump to trip, which caused the turbine to trip, which caused the reactor to automatically shut down, exactly as designed. Within seconds, the control rods were fully inserted and the chain reaction was stopped. So far, everything was working as it should. But here's where the invisible fire shows its treacherous side. Even though the chain reaction was stopped, the fuel was still producing decay heat, the residual heat from the radioactive decay of fission products. This decay heat is not something you can turn off. It's a consequence of the accumulated radioactive materials in the fuel, and it decreases over time but takes hours and days to taper off. Immediately after shutdown, a large reactor produces roughly 7% of its full thermal output from decay heat alone. For a reactor producing 2,800 megawatts thermal, that's nearly 200 megawatts of heat. You have to keep cooling the fuel even after the chain reaction has stopped, or the fuel will overheat and be damaged. The emergency core cooling system activated, pumping water into the reactor to remove the decay heat.
But then a second problem appeared. A pressure relief valve on top of the reactor vessel had opened during the initial transient to vent excess pressure, which was correct behavior. But when the pressure dropped back to normal, the valve was supposed to close. It didn't. It stuck open, and pressurized primary coolant began draining out through the stuck valve, spilling into the containment building. And this is where the invisibility became lethal. The operators in the control room didn't know the valve was stuck open. The indicator on their control panel showed the signal that had been sent to the valve to close, not the actual position of the valve. The instrument was telling them what the valve had been told to do, not what it was actually doing. A crucial distinction. The operators believed the valve was closed. It wasn't. And because they couldn't see the valve, couldn't feel the water draining away, couldn't hear the coolant escaping, they relied on the instrument, and the instrument lied. For over 2 hours, the operators struggled with conflicting instrument readings, trying to understand why the reactor was behaving in ways they didn't expect. Some instruments were telling them there was too much water in the reactor. Other indications suggested the opposite. The conflicting signals were confusing, and the operators, trained on a set of procedures that didn't fully account for this particular combination of failures, made a fateful decision. They turned off the emergency cooling pumps, believing that the reactor had too much water. In reality, the reactor was losing water through the stuck valve and desperately needed more. The core began to overheat. Without adequate cooling, the zirconium cladding on the fuel rods reached temperatures high enough to react with the steam, producing hydrogen gas and further damaging the cladding. The fuel pellets inside the rods began to melt. Roughly half the core suffered severe damage. A partial meltdown. Radioactive gases were released into the containment building, and small amounts of radioactive gas were vented into the atmosphere. The accident was eventually brought under control. No one was killed. The radiation exposure to the surrounding population was extremely small, well below levels associated with any measurable health effects. But the psychological impact was enormous. The accident happened just 12 days after the release of the film The China Syndrome, which depicted a fictional nuclear accident, and the combination of the film and the real event produced a wave of public anxiety about nuclear power that the industry has never fully recovered from. What 3 Mile Island revealed, fundamentally, was a failure of visibility. The operators couldn't see the stuck valve. The instruments didn't show the true state of the system. The training hadn't prepared them for this specific combination of failures, and the result was a cascading series of wrong decisions, each one reasonable given the information available, each one making the situation worse. After TMI, the nuclear industry underwent a profound transformation. Control room designs were overhauled. Operator training was revolutionized. New requirements were imposed for simulator-based training, for human factors engineering, for the design of instrumentation and control panels. The lesson was clear. When you're managing an invisible process, the quality of your instruments and the training of your operators are not just important, they are everything. Chernobyl. April 26, 1986. Chernobyl was a fundamentally different kind of accident.
Where TMI was a failure of operator information in a reactor with fundamentally sound physics, Chernobyl was a failure of reactor design, compounded by operator error and a culture of secrecy and complacency. The Chernobyl reactor was an RBMK, a Soviet design that was very different from the Western PWRs and BWRs we discussed earlier. The RBMK used graphite as a moderator and water as a coolant, with the water flowing through individual pressure tubes rather than filling a single large pressure vessel. The design had several advantages. It could be refueled while operating. It didn't require an expensive and technically challenging large pressure vessel, and it could use natural uranium fuel without enrichment. But the RBMK had a critical flaw, a flaw that was invisible in the sense that it wasn't apparent during normal operation, but lurked in the physics of the reactor, like a hidden fault line. At low power levels, the reactor had a positive void coefficient.
I need to explain this because it matters enormously. Remember how we discussed that in a PWR, if the water boils and forms steam bubbles, known as voids, the loss of moderating effect slows the reaction down. That's a negative void coefficient, and it's a built-in safety feature. The RBMK, because it used graphite rather than water as the primary moderator, behaved differently. In the RBMK, the water served mainly as a coolant, not as the primary moderator. The graphite moderated the neutrons regardless of whether the water was liquid or steam. So when water boiled in the RBMK and formed steam voids, you lost coolant, but you didn't lose your moderator. What you did lose was the neutron absorption that the liquid water had been providing. Water absorbs some neutrons, and when it turns to steam, that absorption decreases. So you had more neutrons available for fission, which meant more power, which meant more boiling, which meant even more power. A positive feedback loop.
Instead of the reactor tamping itself down when things got hot, it pushed itself harder. The hotter it got, the faster it went. The opposite of what you want. Soviet nuclear engineers knew about this characteristic. They had designed procedures to work around it, and the reactor was considered safe as long as it was operated within specific parameters. Operating at low power, where the positive void coefficient was most dangerous, was restricted. But on the night of April 26, 1986, a team of operators was conducting a test of the reactor's electrical systems. And to set up the test, they took the reactor to a very low power level, precisely the regime where the positive void coefficient was most hazardous. The test had been planned for months, and there had been delays and schedule changes that meant the test was being conducted by the night shift, a less experienced crew than originally planned.
The operators, under pressure to complete the test, disabled several safety systems that they felt might interfere with the procedure. They were, in effect, systematically removing the barriers that had been designed to protect against exactly the scenario they were creating. At 1:13 in the morning, the operators attempted to increase the reactor's power from a very low level. The reactor surged. The positive void coefficient did exactly what the physics predicted. Steam formed in the cooling channels, neutron absorption dropped, fission increased, more heat was produced, more steam formed, more fission, more heat, more steam. The power spiked by a factor of hundreds in a matter of seconds, far beyond the reactor's design limits. The operators hit the emergency shutdown button, called AZ5, which was supposed to drive all the control rods into the core and stop the reaction.
But the RBMK's control rods had another design flaw. The tips of the rods were made of graphite, a moderator. When the rods first entered the core, the graphite tips actually increased the reactivity briefly before the neutron-absorbing part of the rod reached the core. Under normal conditions, this brief spike was negligible. But with the reactor already in an unstable state, the momentary increase in reactivity from the graphite tips was enough to push the power even higher. The reactor went prompt critical, a condition where the chain reaction is sustained entirely by prompt neutrons, the ones released instantaneously during fission, without needing the delayed neutrons that normally provide the slight lag that makes reactors controllable. The power surged to roughly 100 times the reactor's normal full power. The fuel disintegrated. The pressure in the cooling channels exceeded their design limits by an enormous margin.
2 explosions destroyed the reactor, blowing the 1,000-ton upper biological shield plate into the air and ripping the reactor building apart. The explosion was not a nuclear detonation. A nuclear reactor cannot produce a nuclear explosion in the sense of a bomb, because the fuel is not sufficiently enriched and the geometry is wrong. The explosions at Chernobyl were a steam explosion and a hydrogen explosion. But the result was that the reactor core, with all its radioactive contents, was blown open and exposed to the atmosphere. The graphite moderator caught fire, and the invisible became visible in the most horrifying way possible. A plume of radioactive material rose into the sky and spread across Europe, carried by the wind, invisible, undetectable by any human sense, settling on fields and forests and cities, contaminating food and water and soil across an area of thousands of square miles.
Chernobyl killed 31 people directly, mostly firefighters and plant workers who received lethal doses of radiation in the first hours and days. The long-term health effects are harder to quantify and remain controversial, but the most clearly documented consequence is an increase in thyroid cancer among children who were exposed to radioactive iodine, particularly those who drank contaminated milk. An area of roughly 1,000 square miles around the plant was evacuated and remains largely uninhabited to this day, though wildlife has returned in abundance and the exclusion zone has become a strange, accidental nature reserve. The Chernobyl accident was, at its heart, a failure to respect the invisible. The RBMK's positive void coefficient was a known characteristic, but it was treated as a manageable quirk rather than a fundamental danger. The operators disabled safety systems because they viewed the test as routine. The institutional culture of the Soviet nuclear industry discouraged questioning and dissent, so the design flaws that had been identified by some engineers were never addressed. And when the invisible fire escaped, it escaped on a scale that no one had prepared for. Fukushima Daiichi, March 11, 2011. The Fukushima accident was different from both TMI and Chernobyl. It was not caused by operator error or design flaws in the normal sense. It was caused by nature, by an event so extreme that it overwhelmed the defenses that had been built to contain the invisible fire. On March 11, 2011, a magnitude 9 earthquake struck off the coast of northeastern Japan. It was one of the most powerful earthquakes ever recorded, and the Fukushima Daiichi nuclear power station, located on the coast about 160 miles northeast of Tokyo, experienced ground shaking well beyond its design basis. The reactors that were operating at the time automatically shut down when the earthquake struck. The control rods inserted and the chain reactions stopped. The earthquake damaged the external power grid, cutting off the plant's normal electricity supply, but this was anticipated. Emergency diesel generators started up and began powering the cooling systems that were needed to remove decay heat from the shutdown reactors. So far, the plant was coping with the earthquake as designed. The problem was what came next. About 50 minutes after the earthquake, a massive tsunami struck the coast. The waves that hit Fukushima Daiichi were roughly 46 feet high. The plant's original design basis assumed a maximum tsunami of about 19 feet, and the seawall had been built to roughly 33 feet. But the waves that struck were nearly 46 feet, roughly 14 feet higher than the wall.
They overtopped it, flooded the lower areas of the plant, and drowned the emergency diesel generators. Without the diesels, there was no power to run the cooling pumps. Without the cooling pumps,
there was no way to remove the decay heat from the reactor cores. This was the nightmare scenario that nuclear safety engineers call a station blackout. Complete loss of all electrical power, both from the grid and from on-site emergency generators. The reactors had shut down correctly, but the fuel was still hot, still producing decay heat, and there was no way to cool it. Over the next several days, the fuel in 3 of the 6 reactors at the site overheated. The zirconium cladding reacted with steam, producing hydrogen gas. The fuel melted, slumping to the bottom of the reactor vessels, and in some cases, melting through the bottom of the vessels and pooling on the floor of the containment structures. Hydrogen accumulated in the reactor buildings and, in 3 cases, exploded, blowing apart the upper structures of the buildings and releasing radioactive material into the environment. The explosions were dramatic and visible, broadcast on television around the world. But the real danger, as always, was invisible. The radioactive contamination that spread through the air and settled on the land and sea around the plant. An area of roughly 310 square miles was evacuated, displacing roughly 154,000 people. No one died from radiation exposure. The physical health effects of the released radiation are expected to be very small, possibly unmeasurable against the background rate of cancer. But the social and psychological impacts were enormous. Destroyed communities, lasting displacement, enduring fear. What Fukushima revealed was that even a well-designed reactor with multiple safety systems can be overwhelmed by an external event that exceeds the design basis. The defenses had been built to handle earthquakes and tsunamis up to a certain magnitude. The actual event was bigger. The question after Fukushima was not whether nuclear energy is safe in some absolute sense, because no energy source is absolutely safe, but whether the industry had adequately anticipated the range of threats it might face. The answer clearly was that it had not. And the response was a global reassessment of nuclear safety, with new requirements for what the industry calls beyond design basis events. Events more extreme than those the plant was originally designed to withstand. 3 accidents, 3 different causes, 3 different failures, but one common thread running through all of them. The invisible fire is unforgiving of complacency. It does not warn. It does not announce itself. It does not give you a second chance to notice that something is wrong. When the barriers fail, when the instruments go blind, when the assumptions prove wrong, the invisible fire does what fire has always done. It burns, silently, relentlessly, and by the time you can see the consequences, the damage is already done. But that common thread has a positive side too, because each of these accidents produce profound changes in the way the nuclear industry operates. And the story of those changes, the story of how humans learn to build ever more sophisticated defenses against an invisible threat, is one of the most impressive examples of institutional learning in the history of technology. Let's talk about that. There is one detail about the Chernobyl disaster that I want to add, because it captures the horror and the heroism of dealing with an invisible fire that has escaped its containment. In the hours after the explosion, the immediate danger was not just the radiation escaping from the destroyed reactor, but the possibility that the molten core material, the corium, a hellish mixture of melted fuel, cladding, and structural materials at temperatures exceeding 3,600 degrees Fahrenheit, could burn through the concrete floor of the reactor building and reach the water in the suppression pools beneath it. If the corium contacted that water, the resulting steam explosion could have been catastrophic, potentially destroying the other reactors at the site and releasing many times more radioactive material into the atmosphere. To prevent this, someone had to drain the water from the suppression pools, manually, by opening valves in flooded, pitch-dark corridors beneath the destroyed reactor, in an environment saturated with radiation levels that could deliver a fatal dose in minutes. 3 men volunteered: Alexei Anonenko, Valery Bespalov, and Boris Baranov. They waded through radioactive water in near-total darkness, guided by a single flashlight, found the valves, and opened them, allowing the water to drain. They emerged alive. The popular narrative that they died shortly afterward from radiation exposure is, according to most sources, incorrect. Anonenko and Bespalov were alive and gave interviews decades later. Baranov died in 2005 of a heart attack. But the fact remains that they went into a place that they had every reason to believe would kill them, to deal with a threat that they could not see, hear, or feel, guided only by their understanding of the invisible processes at work and their willingness to trust that understanding with their lives. And in the weeks and months that followed, thousands of workers, called liquidators, were brought in to clean up the disaster. They worked in shifts measured in seconds and minutes rather than hours, sprinting onto the roof of the adjacent reactor building to shovel chunks of radioactive graphite and fuel back into the destroyed reactor, then sprinting away before their accumulated dose exceeded the limit. Many of them were young soldiers, ordered to do the work, given minimal protective equipment, and told very little about the risks they faced. The radiation was invisible. They could not feel it. They could not see the graphite glowing or the fuel fragments radiating. They picked up pieces of the reactor core with their gloved hands and threw them off the roof, working in a lethal environment that looked to the naked eye like an ordinary construction site littered with rubble. The liquidators built the original sarcophagus, the concrete shelter that was hastily constructed over the destroyed reactor in the months following the accident. It was built under extraordinary conditions, with workers limited to minutes of exposure at a time, using remote-controlled equipment where possible and human labor where it wasn't. The sarcophagus was never intended to be a permanent solution. It was a patch, a stopgap, a way to contain the worst of the contamination while a more permanent solution was devised. That permanent solution, the new safe confinement, was completed in 2016. It is the largest movable structure ever built. A steel arch roughly 355 feet tall, 530 feet long, and 840 feet wide, weighing 36,000 tons. It was assembled on rails next to the destroyed reactor and then slid into position over the old sarcophagus, a journey that took several days. Inside, it contains cranes and robotic systems that will eventually be used to dismantle the destroyed reactor and remove the radioactive debris. The process is expected to take decades and cost billions. All of this effort, all of this expense, all of this ingenuity to contain the consequences of a few seconds of uncontrolled, invisible fire. The invisible fire, once escaped, demands a price that is measured not in days but in decades, not in millions but in billions, not in square feet but in square miles. After Chernobyl, after Fukushima, after 3 Mile Island, a reasonable person might ask, why bother? If nuclear energy is this difficult, this demanding, this unforgiving of error, why not just use something else? Burn gas, build solar panels, put up wind turbines. Why take on the burden of managing an invisible fire that can contaminate vast areas of land for decades if something goes wrong? It's a fair question, and to answer it honestly, you have to look at what the nuclear industry did after each of those accidents. Because the response to failure tells you more about a technology than the failure itself.
After 3 Mile Island, the nuclear industry created something called the Institute of Nuclear Power Operations, or INPO. INPO is, in effect, a self-policing body for the American nuclear industry, and its creation represented a fundamental shift in thinking. Before TMI, nuclear safety was largely the responsibility of individual utilities and the government regulator. After TMI, the industry recognized that a single bad actor could damage the reputation and viability of every nuclear plant in the country, and they created INPO to enforce standards across the entire industry. INPO conducts rigorous inspections of every nuclear plant in the United States, evaluating everything from equipment maintenance to operator training to safety culture. Its evaluations are detailed, blunt, and consequential. A bad INPO rating can lead to increased regulatory scrutiny, higher insurance costs, and intense pressure from industry peers. The standards INPO enforces are, in many cases, more demanding than the legal requirements imposed by the Nuclear Regulatory Commission. The concept of safety culture, which seems obvious now, was largely crystallized in the nuclear industry after Chernobyl. The International Atomic Energy Agency, the IAEA, defined safety culture as the assembly of characteristics and attitudes in organizations and individuals that establishes that nuclear safety issues receive the attention warranted by their significance. What that means in practice is a set of behaviors and expectations, that anyone can raise a safety concern without fear of retaliation, that procedures are followed rigorously even when they seem unnecessary, that deviations from normal are investigated thoroughly even if they seem trivial, that complacency is treated as the most dangerous threat of all. This last point is worth dwelling on. The sociologist Diane Vaughan, studying the Space Shuttle Challenger disaster, coined the term normalization of deviance to describe a process by which organizations gradually come to accept abnormal conditions as normal. A warning sign appears, but nothing bad happens, so the warning is downgraded. A procedure is skipped for convenience, and no consequence follows, so skipping it becomes routine. A parameter drifts outside its normal range, but everything still works, so the range is mentally expanded to include the new value. Over time, the organization's definition of normal shifts imperceptibly toward a state that the original designers would have recognized as dangerous. This is exactly what happened at Chernobyl, where a culture of routine safety violations had eroded the barriers that were supposed to prevent exactly the accident that occurred.
It is, in some form, what happened at Fukushima, where the assumption that a tsunami of a certain maximum height was adequate protection was maintained even after geological evidence suggested that larger tsunamis had occurred in the area historically. And it is the failure mode that the nuclear industry now works hardest to prevent, because it is the most insidious, the slow, invisible erosion of vigilance that happens when nothing has gone wrong for a long time, and people start to believe that nothing ever will. The engineering response to these lessons has been equally profound. Modern reactor designs incorporate what is called defense in depth, a philosophy of multiple independent barriers and safety systems, each one capable of preventing a release of radioactive material even if the others fail. Let me walk you through the layers, because the architecture is impressive. The first barrier is the fuel itself. The uranium dioxide fuel pellets are ceramic, with very high melting points, roughly 5,000 degrees Fahrenheit. They are designed to retain most fission products within their crystal structure, even under extreme conditions. The fuel pellet itself is a barrier. The second barrier is the fuel cladding, the zirconium alloy tubes that encase the fuel pellets. As long as the cladding is intact, the radioactive fission products inside the fuel rods cannot escape into the coolant water. The cladding is designed to withstand the temperatures, pressures, and radiation levels inside the reactor for years without failing. The third barrier is the reactor coolant system boundary, the piping, pumps, and vessel that contain the pressurized coolant water. This is a sealed system, welded and inspected and tested to extraordinary standards. The fourth barrier is the containment building, a massive structure of reinforced concrete and steel that surrounds the entire reactor system. A typical containment building has walls 3 to 4 feet thick, made of pre-stressed concrete with a steel liner. It is designed to withstand internal pressures from a loss of coolant accident, external impacts from tornadoes and hurricanes and aircraft crashes, and seismic events. The containment building is the last engineered barrier between the invisible fire and the outside world. Each of these barriers is independent. A failure of one does not necessarily cause a failure of the next. The fuel pellet can fail without breaching the cladding. The cladding can fail without breaching the coolant system boundary. The coolant system can fail without breaching the containment. To get a release of radioactive material to the environment, you need to breach all 4 barriers, and each one is designed and maintained to standards that make individual failure unlikely, let alone simultaneous failure of all 4. After Fukushima, a new layer of defense was added, FLEX equipment, which stands for Diverse and Flexible Coping Strategies. FLEX is essentially a collection of portable pumps, generators, hoses and batteries that can be deployed to any reactor in the event that all installed safety systems fail. The idea is that even if an event overwhelms every designed safety system at the plant, there will still be portable equipment available to cool the reactor and maintain containment. This equipment is stored in hardened buildings designed to withstand extreme natural events, and plant operators are trained regularly in its deployment. The philosophy behind all of this is simple but demanding. Assume failure. Assume that any individual system can fail. Assume that multiple systems can fail simultaneously. Assume that the event will be worse than anything you've imagined, and then design your defenses so that even under those worst-case assumptions, the invisible fire stays contained.
There's an old phrase in engineering that captures this. Belt and suspenders, and then staple your pants to your shirt for good measure. Nuclear safety engineering takes that philosophy to its logical extreme, adding layer upon layer of protection, each one independent, each one sufficient by itself, each one designed with the assumption that all the other layers have already failed. And beyond the hardware, beyond the concrete and steel and redundant pumps, there is the human element, the culture of vigilance that the industry has built, often painfully, often in response to failure. Over 70 years of operating experience. The daily briefings, the peer reviews, the corrective action programs, the near-miss investigations, the regulatory inspections, the INPO evaluations, the IAEA peer reviews, the continuous training and retraining and testing and retesting. All of it designed to combat the normalization of deviance, to keep operators and managers and engineers and regulators alert to the invisible dangers that never announce themselves. Is it perfect? Of course not. Perfection is not a human achievement. But the nuclear industry's safety record, measured in terms of harm per unit of energy produced, is among the best of any energy source. Statistically, nuclear power causes fewer deaths per terawatt-hour of electricity generated than coal, oil, natural gas, biomass, or even rooftop solar, which has a surprisingly significant rate of fatal falls during installation. The invisible fire is dangerous, undeniably. But the visible fires that we've been burning for centuries are dangerous too, in ways that are less dramatic but ultimately more destructive. Coal-fired power plants release not only carbon dioxide, but also particulate matter, sulfur dioxide, nitrogen oxides, mercury, and other pollutants that cause respiratory and cardiovascular disease. The World Health Organization estimates that air pollution from fossil fuel combustion kills roughly 4.5 million people every year worldwide. That's equivalent to a Chernobyl every few hours, around the clock, year after year, decade after decade. But because the deaths are dispersed,
gradual and invisible in the sense that you can't point to any single death and say, coal smoke did this. They don't generate the same fear and outrage as a nuclear accident. The irony is almost unbearable. The visible fires kill invisibly through dispersed, chronic, accumulated harm that never makes headlines. The invisible fire kills visibly through dramatic, localized, acute events that dominate the news for weeks and shape public perception for decades.
The danger that we can see frightens us less than the danger we cannot see, even when the danger we can see is doing far more damage. And that is perhaps the deepest lesson of the invisible fire. Our fear is not proportional to the risk. Our fear is proportional to the invisibility. We fear what we cannot perceive, cannot understand, cannot control with our senses. And managing that fear, learning to trust the instruments and the engineering and the institutional discipline that make nuclear energy safe, is as much a psychological challenge as it is a technical one. But the engineers and physicists who work in nuclear energy are not content with the current state of affairs. They are designing new reactors, new systems, new approaches that promise to make the invisible fire safer, more efficient, and more accessible than ever before.
And some of those designs are so elegant, so deeply rooted in the fundamental physics of the atom, that they represent a genuine leap forward in humanity's long quest to harness energy from the unseen world. Before we look at the future, let's step back and trace the full journey of nuclear fuel, from the moment it's pulled out of the ground to the moment it's sealed away forever. Because this journey, the nuclear fuel cycle, is one of the most remarkable stories of transformation in all of industry, and every step of it involves managing invisibility. It starts in the earth. Uranium ore is mined from deposits around the world, in countries like Kazakhstan, Canada, Australia, Namibia, and Niger. Uranium is not especially rare. It's about as common as tin in the Earth's crust, but it's scattered. The ore typically contains only a fraction of a percent of uranium by weight, mixed with ordinary rock and soil. The first step is to extract the uranium from the ore, which is done through a series of chemical processes, crushing the rock, dissolving it in acid or alkali, purifying the solution, and precipitating out a concentrated uranium compound called yellow cake. Yellow cake is a coarse powder, yellow or brownish, and it contains roughly 70 to 90% uranium oxide. But yellow cake is not fuel. Natural uranium, as we've discussed, is almost entirely uranium-238, with only 0.7% of the fissile uranium-235. For most commercial reactors, that proportion needs to be increased, enriched, to somewhere between 3 and 5% uranium-235. And enrichment is one of the most technically challenging and politically sensitive processes in the entire nuclear enterprise. The reason enrichment is so difficult is that uranium-235 and uranium-238 are chemically identical. They are the same element. They differ only in the number of neutrons in their nuclei, which gives them slightly different masses. 235 versus 238 atomic mass units. Separating them based on that tiny mass difference is like trying to sort a pile of baseballs into slightly heavier and slightly lighter categories, where the difference in weight is about 1%. The dominant enrichment technology today is the gas centrifuge. Uranium is converted into a gas, uranium hexafluoride, and that gas is fed into a rapidly spinning cylinder. The heavier uranium-238 molecules tend to move outward toward the wall of the cylinder, while the lighter uranium-235 molecules remain slightly closer to the center. By skimming off the gas from different positions within the centrifuge, you can produce two streams. One slightly enriched in uranium-235 and one slightly depleted.
The enrichment per centrifuge is tiny, so you need cascades of thousands of centrifuges, each one feeding into the next, to build up the enrichment to the level needed for reactor fuel. These centrifuges spin at extraordinary speeds, up to 70,000 revolutions per minute or more, creating centrifugal forces hundreds of thousands of times greater than gravity. The engineering tolerances are extreme. The rotors must be perfectly balanced, made from exotic materials like carbon fiber or miraging steel. A single imbalance can destroy the centrifuge. And because the same technology can be used to enrich uranium beyond the levels needed for reactor fuel, all the way up to the 90% or more needed for weapons, enrichment technology is among the most tightly controlled in the world. The spread of centrifuge technology is a proliferation concern, and international inspections by the IAEA are designed to verify that enrichment facilities are producing only low-enriched uranium for civilian power, not highly enriched uranium for weapons. Once enriched, the uranium hexafluoride is converted to uranium dioxide powder, which is pressed and sintered into those small ceramic pellets we discussed earlier. The pellets are loaded into zirconium alloy tubes to make fuel rods. The rods are bundled into fuel assemblies, and the assemblies are loaded into the reactor core. A fuel assembly typically stays in the reactor for about 4 to 6 years, during which the uranium-235 in the fuel is gradually consumed by fission. By the end of its life, the fuel contains a complex mixture of materials, remaining uranium-235 and 238, plutonium produced by neutron capture in uranium-238, and a wide variety of fission products, the fragments left behind when uranium and plutonium atoms split. Some of these fission products are highly radioactive and will remain dangerous for decades or centuries. Others are radioactive but decay quickly. A few are stable and harmless. When a fuel assembly is removed from the reactor, it is intensely radioactive and produces significant decay heat. It is placed in the spent fuel pool, a deep pool of water adjacent to the reactor building, where the water serves both as a radiation shield and as a coolant to remove the decay heat. The spent fuel stays in the pool for at least several years, sometimes decades, while the most intensely radioactive short-lived fission products decay away. This is where you would see the Cherenkov radiation we discussed earlier, that haunting blue glow from the most recently discharged fuel. After sufficient cooling, the spent fuel can be transferred to dry cask storage, massive steel and concrete containers that hold the fuel assemblies and provide shielding and passive cooling through natural air circulation. These casks are engineered to be extraordinarily robust. They can withstand collisions, fires, drops, and even direct hits from heavy projectiles without releasing their contents. They sit on concrete pads at the reactor site, silent and motionless, containing their invisible cargo for decades. And here is where the nuclear fuel cycle encounters its most challenging question. What happens next? What do you do with spent nuclear fuel that will remain dangerously radioactive for thousands of years? There are two main approaches, and the choice between them is one of the most consequential decisions in the entire nuclear enterprise. The first approach is the once-through cycle, also called open fuel cycle. In this approach, the spent fuel is treated as waste. It is stored, eventually it will be placed in a deep geological repository, and it is left there, permanently, sealed away from the biosphere for the tens of thousands of years needed for the radioactivity to decay to safe levels. This is the approach currently favoured by the United States, Sweden, and Finland. Finland, as we mentioned, is building the world's first operational deep geological repository called Onkalo on the island of Olkiluoto.
The repository is being excavated in bedrock that is roughly 1.8 billion years old, rock that has been geologically stable for almost half the age of the Earth. The spent fuel will be sealed in copper canisters, surrounded by bentonite clay, and placed in tunnels roughly 1,300 feet below the surface. The facility is designed to isolate the waste for at least 100,000 years.
100,000 years. That number is worth sitting with. The oldest known cave paintings are roughly 40,000 years old. Written language is about 5,000 years old. The oldest surviving human structures are maybe 10,000 years old. 100,000 years is a span of time that utterly dwarfs all of human civilization. The engineers who designed Onkolo had to grapple with questions that no engineers have ever faced before. Will the rock remain stable? Will the copper canisters corrode? Will groundwater carry radioactive material upward? And most eerily, how do you warn people who might live 100,000 years from now, who might speak no language we recognize, who might have no concept of radioactivity, that there is something dangerous buried here? The second approach is reprocessing, also called the closed fuel cycle. In this approach, the spent fuel is chemically processed to extract the remaining uranium and plutonium, which are recycled into new fuel. France is the leading practitioner of reprocessing, operating a large reprocessing plant at La Hague in Normandy. Reprocessing reduces the volume and toxicity of the final waste because the recovered uranium and plutonium, which account for most of the long-lived radioactivity, are put back into the fuel cycle rather than being treated as waste. The remaining waste, primarily fission products, is vitrified, meaning it's mixed with molten glass, and the resulting glass logs are stored for eventual disposal. Reprocessing is controversial. Supporters argue that it reduces waste and extends the fuel supply. Critics point out that it is expensive, that it produces separated plutonium, which is a proliferation concern, and that the economic case for reprocessing is weak as long as uranium remains cheap. The debate has been going on for decades and shows no signs of being resolved anytime soon. Whether you favor the open cycle or the closed cycle, one thing is clear: the back end of the nuclear fuel cycle is the hardest part. Not technically necessarily, but politically, socially, and psychologically. Because the waste is invisible. You can't see the radiation, you can't feel the danger, and asking communities to accept a waste repository in their neighborhood, asking them to trust that engineered barriers will hold for 100,000 years, is asking for a level of trust that goes far beyond anything else in the modern energy economy. It is asking people to trust not just the current generation of engineers and regulators, but all the generations to come. And that trust, fragile and hard-won, is what the future of nuclear energy depends on. So where does the invisible fire go from here?
The reactors operating today are overwhelmingly second and third generation designs, descendants of the technology that was originally developed for nuclear submarines in the 1950s. The pressurized water reactor, the dominant design worldwide, traces its lineage directly to the reactors that Hyman Rickover's team designed for the USS Nautilus, the world's first nuclear-powered submarine, which went to sea in 1955. That design was chosen for submarines because water was readily available as a coolant. The technology was compact enough to fit inside a submarine hull, and the US Navy already had extensive experience with pressurized steam systems. When the time came to build civilian power plants, the submarine reactor design was scaled up and adapted. It worked. It was proven. It was what the engineers knew how to build. But it was not the only possibility, and it was arguably not even the best possibility. Throughout the 1950s and 60s, a remarkable diversity of reactor designs were explored. Reactors cooled by sodium, by helium, by molten salt, by heavy water. Reactors that ran on thorium instead of uranium.
reactors that could breed new fuel from non-fissile materials, producing more fuel than they consumed. Many of these designs showed extraordinary promise. Some were built and operated successfully for years, but the momentum of the PWR, its proven track record, the infrastructure already built around it, the regulatory frameworks already established for it, all of these forces conspired to make the PWR the default choice for new construction. The alternatives were pushed to the margins, kept alive in research programs, but never commercially deployed. Now, 60 years later, several of those alternative designs are being revived, updated with modern materials and manufacturing techniques and computational tools, and offered as the next generation of nuclear power.
They're called Generation 4 reactors, and some of them address the most fundamental criticisms of current nuclear technology. Let me tell you about a few of them. The molten salt reactor is one of the most intriguing. Instead of solid fuel rods cooled by water, a molten salt reactor dissolves its nuclear fuel directly in a liquid salt mixture that also serves as the coolant. The salt, typically a mixture of fluoride salts, has excellent heat transfer properties and operates at atmospheric pressure, which eliminates the need for the massive pressure vessels that PWRs require. Because the fuel is dissolved in the coolant, the reactor has some remarkable safety properties. If the reactor overheats, the salt expands, which reduces the nuclear reaction rate through negative feedback.
If the reactor loses power entirely, a frozen plug at the bottom of the reactor vessel melts, and the fuel salt drains by gravity into a tank where it spreads out and cools down naturally, without any operator action or any powered systems. The invisible fire puts itself out. The original molten salt reactor experiment ran at Oak Ridge National Laboratory in the United States from 1965 to 1969. It worked beautifully, but it was shut down, partly because the Atomic Energy Commission chose to focus its resources on fast breeder reactors instead, and partly because the molten salt program's champion, Alvin Weinberg, was dismissed from Oak Ridge after he publicly questioned the safety of light water reactors in the early 1970s. The technology was shelved for decades. Now it's coming back. Several companies in the United States, Canada, and China are developing modern versions of the molten salt reactor, incorporating decades of advances in materials science, computer modeling, and manufacturing technology. Some of these designs can use thorium as a fuel, which is roughly 4 times more abundant than uranium in the Earth's crust and produces far less long-lived radioactive waste. Others can actually consume existing nuclear waste, using spent fuel from conventional reactors as their feedstock and burning down the long-lived actinides that are the primary concern in waste disposal. Another promising design is the high-temperature gas-cooled reactor, which uses helium gas instead of water as the coolant and graphite as the moderator. The fuel in these reactors takes the form of tiny coated particles, each one a sphere about the size of a poppy seed, containing a kernel of uranium surrounded by multiple layers of ceramic coating that serve as miniature containment vessels. These coated particles, called trisoparticles, are then formed into larger fuel elements, either spheres about the size of a tennis ball, called pebbles, or prismatic blocks. The beauty of triso fuel is its robustness. Each particle is its own containment system, and the ceramic coatings can withstand temperatures far beyond anything the reactor would reach, even in the most extreme accident scenarios. In testing, triso fuel has been heated to over 2,900 degrees Fahrenheit without releasing significant amounts of radioactive material. Because the gas coolant operates at very high temperatures, up to roughly 1,600 degrees Fahrenheit or more, These reactors can not only generate electricity with high efficiency, but also provide high-temperature heat for industrial processes that currently rely on fossil fuels. Hydrogen production, desalination, chemical manufacturing, steel production. This opens up the possibility of using nuclear energy to decarbonize not just electricity, but industry as well, which is responsible for roughly a quarter of global carbon dioxide emissions. And then there are small modular reactors, or SMRs, which represent a different kind of innovation. Instead of building ever larger reactors, the SMR concept is to build smaller ones, typically 300 megawatts electrical or less, compared to 1,000 megawatts or more for a conventional large reactor. The key advantage is that smaller reactors can be manufactured in factories and transported to the site, rather than being built from scratch on site, as conventional reactors are. Factory manufacturing allows for tighter quality control, shorter construction times, and lower financing costs. It also allows nuclear power to be deployed in smaller grids and more remote locations where a large conventional reactor would be impractical or uneconomical. Several SMR designs are in advanced stages of development. Some are scaled-down versions of conventional PWRs. Others use entirely different technologies: molten salt, sodium cooling, gas cooling. What they share is a philosophy of designing safety into the physics, rather than relying on active engineered systems. Many SMR designs are walk-away safe, meaning that if all power is lost and all operators walk away, the reactor will shut itself down and cool itself through natural processes, without any human intervention, without any powered systems, without any action at all. The invisible fire in these designs has been tamed to such a degree that it will put itself out if left alone. And beyond fission, there is fusion. Nuclear fusion is the process that powers the sun. Instead of splitting heavy atoms like uranium, fusion combines light atoms, typically isotopes of hydrogen, into heavier ones, releasing enormous amounts of energy in the process. Fusion produces no long-lived radioactive waste, generates no fission products, and poses no risk of a meltdown because the reaction requires such extreme conditions that any disruption instantly stops the process. The fuel, deuterium and tritium, can be obtained from seawater and lithium, making it effectively inexhaustible. The challenge of fusion is that replicating the conditions inside a star on Earth is extraordinarily difficult. You need to heat the fuel to over 200 million degrees Fahrenheit, roughly 10 times the temperature at the center of the Sun, and confine it long enough for the fusion reactions to occur. The two main approaches use either powerful magnetic fields, in devices called tokamaks, or intense laser beams to compress and heat tiny pellets of fuel. Fusion has been the energy source of the future for roughly 70 years, and skeptics enjoy pointing out that it always seems to be 30 years away. But recent advances have been significant. In December 2022, the National Ignition Facility in the United States achieved fusion ignition for the first time, producing more energy from a fusion reaction than was delivered to the fuel by the lasers. It was a scientific milestone, though turning it into a practical power source will require solving enormous engineering challenges. Meanwhile, the International ITER project in southern France, the largest tokamak ever built, is moving toward its first experiments, though it has been plagued by delays and cost overruns. Whether fusion will eventually become a practical energy source is still an open question. But if it does, it will represent the ultimate invisible fire. Energy produced by forcing invisible atoms together at invisible temperatures inside invisible magnetic bottles, producing invisible neutrons that heat invisible lithium blankets, that boil invisible water, that spins invisible turbines. Every step of the process even more removed from human perception than fission already is. Every step demanding even greater trust in instruments, in engineering, in the institutional disciplines that keep the invisible fire contained. And maybe that's the trajectory of human civilization's relationship with energy. From the visible to the invisible,
from the tangible to the abstract, from the fire you can see and feel and hear, to the fire that exists only as numbers on a screen, managed by systems that exceed anything a single human being can comprehend. We started with campfires and we may end with contained stars, and the distance between those 2 points is the distance between instinct and trust. Let's talk about scale, because scale is where the invisible fire truly defies ordinary comprehension. A single uranium fuel pellet, that little cylinder the size of a pencil eraser, contains as much energy as about 17,000 cubic feet of natural gas, or 1,780 pounds of coal, or 149 gallons of oil. One pellet.
You could line up a row of these pellets from one end of your desk to the other, and they would contain more energy than several thousand homes use in a year. A typical large nuclear reactor produces about 1,000 megawatts of electrical power. Running at full capacity for a year, it generates roughly 8 billion kilowatt hours of electricity. To produce the same amount of electricity from coal, you would need to burn roughly 3 million tons of coal, a train of coal cars stretching about 34 miles long. To produce it from natural gas, you would need roughly 53 billion cubic feet of gas. To produce it from oil, you would need about 13 million barrels. The nuclear reactor uses roughly 25 tons of enriched uranium fuel. 25 tons versus 3 million tons. The ratio is staggering. And the waste? The spent fuel produced by that reactor in a year, after it has generated 8 billion kilowatt hours of electricity, amounts to roughly 27 tons of spent fuel assemblies. Compare that to the 3 million tons of coal that would have been burned, producing roughly 8 million tons of carbon dioxide, plus fly ash, bottom ash, sulfur dioxide, nitrogen oxides, mercury, and a radioactive waste stream that few people know about, because coal contains trace amounts of uranium and thorium, and burning coal concentrates these materials in the ash and releases some of them into the atmosphere. A coal plant actually releases more radioactivity into the environment per unit of electricity produced than a normally operating nuclear plant. The invisible fire, paradoxically, is less radiologically polluting than the visible fire. These numbers matter because they illuminate the central irony of the nuclear debate. The energy source that people fear the most is, by most objective measures, one of the safest and cleanest available. The energy sources that people accept without question, the coal plants and gas plants and oil refineries that dot every industrial landscape, cause orders of magnitude more harm per unit of energy produced. But the harm from fossil fuels is dispersed, gradual, and invisible in its own way. Invisible particulate matter in the air, invisible carbon dioxide accumulating in the atmosphere, invisible mercury depositing in waterways and accumulating in fish. And because that harm is invisible, it doesn't trigger the visceral fear response that nuclear energy does. Our relationship with nuclear energy is, in the end, a test of our ability to think beyond our instincts, to evaluate risk rationally rather than emotionally, to trust evidence and analysis rather than gut feeling, to accept that the invisible can be managed, that the unseen can be measured, that the incomprehensible can be controlled. If we are willing to build the institutions and maintain the discipline that the task requires. And if that sounds like a lot to ask of a species that spent most of its evolutionary history running from predators and huddling around campfires, well, it is. It is a lot to ask. But then again, so was everything else we've ever done that mattered. Language was a lot to ask. Agriculture was a lot to ask. Medicine was a lot to ask. Every advance that separated us from the animals required us to override our instincts.
to trust in systems and institutions and abstract reasoning rather than in the immediate evidence of our senses. Nuclear energy is simply the latest and perhaps the most dramatic instance of that fundamental human project, the project of learning to trust what we cannot see.
There's one more comparison worth making, because it puts the invisible fire into a context that might surprise you. The total amount of spent nuclear fuel ever produced by the entire United States commercial nuclear fleet, from the very first reactor to today, is roughly 86,000 tons. That sounds like a lot until you realize that it would all fit in a single football field, stacked about 30 feet high. 70 years of electricity generation from over 100 reactors, enough electricity to power the entire United States for about 15 years total, and the waste from all of it fits in a structure the size of a large warehouse. Compare that to the waste from coal. The United States burns roughly 500 million tons of coal per year for electricity generation. The ash alone, the solid residue left after burning, amounts to roughly 130 million tons per year.
In 70 years, that's over 9 billion tons of ash, much of it containing toxic heavy metals like arsenic, cadmium, lead, and mercury, stored in vast ash ponds that occasionally fail, as happened catastrophically at the Kingston fossil plant in Tennessee in 2008, when a dike failure released over 1 billion gallons of coal ash slurry into the Emery River, contaminating hundreds of acres. And the carbon dioxide from coal combustion? The United States coal fleet emits roughly 1 billion tons of CO2 per year. Over 70 years, that's 70 billion tons of carbon dioxide released into the atmosphere, contributing to climate change that is already causing measurable harm to ecosystems and human communities worldwide. That carbon dioxide is invisible too, just as invisible as radiation, and its effects, while slower, are arguably far more destructive on a global scale. The visible fire produces invisible waste that harms the whole planet. The invisible fire produces visible waste that fits in a warehouse. And we fear the warehouse more than we fear the atmosphere. Our instincts evolved over millions of years to detect immediate, visible threats, serve us very poorly in a world where the greatest dangers are invisible, dispersed, and slow. This doesn't mean that nuclear waste is not a serious problem. It is. Managing radioactive materials for thousands of years is a genuine challenge that demands serious engineering and institutional solutions. But it is a manageable challenge, a contained challenge, a challenge with a known scope and defined boundaries. Climate change, by contrast, is an uncontained challenge with no defined boundaries and consequences that are global, irreversible, and accelerating. The invisible fire may be our best tool for fighting an even more invisible fire. The slow, silent, planetary-scale combustion of fossil carbon that is changing the chemistry of the atmosphere and the temperature of the oceans in ways that will affect every living thing on Earth for centuries to come. Let me tell you about something that happened at a nuclear power plant on a completely ordinary Tuesday. Nothing dramatic, nothing newsworthy, nothing that anyone outside the plant would ever know about. A technician was performing a routine inspection of a section of piping in the reactor building. This particular pipe carried primary coolant water, the water that flows through the reactor core and is slightly radioactive. The pipe was made of stainless steel, about 8 inches in diameter, and it had been in service for over 20 years. The inspection involved using an ultrasonic probe, a device that sends sound waves into the metal and listens to the echoes.
By analyzing the echoes, the technician could measure the thickness of the pipe wall to within a few thousandths of an inch, detecting any thinning caused by corrosion or erosion. On this particular Tuesday, the technician found a section where the pipe wall was slightly thinner than expected. Not dangerously thin, not close to failing, just a few thousandths of an inch thinner than the last measurement, taken 2 years earlier. The technician recorded the measurement, filed a report, and the report entered the plant's corrective action program. Over the next several weeks, engineers analyzed the data, compared it with measurements from previous inspections, calculated the rate of wall thinning, and projected how long the pipe could remain in service before the wall would approach the minimum acceptable thickness. They determined that the pipe was safe to continue operating for several more years, but they also scheduled a repair for the next planned outage, just to be safe. They updated the inspection schedule for similar pipes elsewhere in the plant. They reviewed the water chemistry program to see if adjustments could reduce the corrosion rate. They documented everything and shared their findings with other plants of similar design. This entire process, from the initial measurement to the final resolution, took several months and involved dozens of people. It generated hundreds of pages of documentation, and the pipe was never in danger of failing. This is what nuclear safety looks like on a daily basis. Not dramatic, not exciting, not the stuff of headlines or Hollywood movies, just meticulous, relentless, unglamorous attention to detail, applied to thousands of components across hundreds of plants, day after day, year after year, decade after decade. The invisible fire is kept safe not by grand gestures or heroic interventions, but by an almost obsessive culture of measurement, documentation, analysis, and continuous improvement.
And this culture extends far beyond the plants themselves. The nuclear regulatory framework is one of the most elaborate systems of oversight ever devised. In the United States, the Nuclear Regulatory Commission employs roughly 3,000 people, including resident inspectors who are permanently assigned to each nuclear plant. These inspectors have independent authority to shut down a reactor if they believe safety is being compromised. They conduct thousands of inspection hours per plant per year, examining everything from the condition of equipment to the quality of operator training to the thoroughness of maintenance procedures. Internationally, the IAEA conducts peer reviews of national nuclear safety programs through its OSART missions, Operational Safety Review Teams, and its IRRS missions, Integrated Regulatory Review Service.
These reviews bring international experts to a country to evaluate its nuclear safety infrastructure, identify areas for improvement, and share best practices from other countries. The findings are published and followed up, creating a global network of shared learning and mutual accountability. All of this oversight, this layered system of checks and inspections and reviews, exists because of the fundamental nature of the invisible fire. You cannot manage what you cannot see, so you build systems to see it. You cannot trust what you cannot verify, so you build systems to verify it. And you cannot prevent complacency through vigilance alone, so you build systems to ensure that vigilance is institutional, not just individual. There's a phrase that nuclear safety professionals use: chronic unease. It means a persistent low-level discomfort with the state of affairs, a habitual questioning of whether things are really as safe as they seem, a refusal to take safety for granted, even when all the indicators are green. It is, in a sense, the opposite of the normalization of deviance. Where normalization of deviance involves becoming comfortable with risk, chronic unease involves being perpetually uncomfortable with the possibility of risk, even when there is no immediate evidence of it. This is a hard state of mind to maintain. Human beings are not wired for chronic unease. We are wired to habituate, to become accustomed to our environment, to stop noticing things that don't change. A smoke alarm that beeps intermittently stops being alarming after the third beep. A warning light that is always on becomes invisible. The challenge of nuclear safety is to fight this deeply human tendency, to keep the attention sharp, to keep the questions coming, to keep the measurements precise and the analyses thorough, even when everything has been fine for years, even when the last significant event was a generation ago. And this is the invisible bargain that nuclear energy asks us to make. It asks us to trade the visible, tangible, intuitive relationship we have with fire, the fire we can see and feel and understand, for a relationship with an invisible force that we can never perceive directly, that we must manage through instruments and institutions, that demands a level of discipline and vigilance that has no equivalent in any other energy industry. In exchange, it offers energy that is staggeringly concentrated, carbon-free, available around the clock regardless of weather, and safer per unit of electricity produced than any fossil fuel. Whether that bargain is worth making is a question that each society must answer for itself. But the question is increasingly being answered, in the affirmative. As the reality of climate change becomes more urgent, as the limitations of renewable energy become more apparent, as the need for reliable, carbon-free baseload power becomes more pressing, countries around the world are turning to nuclear energy with renewed interest. China is building more nuclear reactors than any other country. India has an ambitious nuclear expansion program. The United Kingdom is building new reactors for the first time in a generation. Even countries that had previously committed to phasing out nuclear power, like Japan and South Korea, are reconsidering. The invisible fire, it seems, may be the fire that the 21st century needs. So, as you lie there, wherever you are, let's just sit with all of this for a moment.
Right now, at this very instant, somewhere on this planet, a nuclear reactor is operating. You will never hear it. You will never see it. You will never feel the faintest tremor from its work. A uranium atom is splitting inside a zirconium tube, inside a steel vessel, inside a concrete containment building, releasing energy that was locked away 4.5 billion years ago, when a dying star scattered heavy elements across a collapsing cloud of dust and gas that would eventually become our solar system. That energy, forged in the violence of a stellar explosion, sealed inside the nucleus of an atom, buried in the Earth's crust, dug up by miners, refined by chemists, enriched by engineers spinning centrifuges at 70,000 revolutions per minute, pressed into a ceramic pellet the size of a pencil eraser, loaded into a tube, submerged in water, and split by a neutron traveling at a few thousand miles per hour. That energy is now heating water. The water is boiling. The steam is spinning a turbine. The turbine is spinning a generator. The generator is pushing electrons through copper wire, and those electrons are traveling through the grid, through transformers and substations and miles of cable, to reach a hospital where a machine is keeping a baby alive, or a home where someone has left a light on because they don't like sleeping in the dark, or a server farm where the message you sent an hour ago is being stored and forwarded and delivered to someone you love. All of it invisible, every step. From the star that forged the uranium to the light that reaches your eyes, the chain of causes is almost entirely invisible to the human beings who benefit from it. And the only reason it works, the only reason the invisible fire stays contained and controlled and productive, is that thousands of people you will never meet are doing their jobs tonight. Operators are watching instruments. Technicians are checking valves. Engineers are analysing data. Inspectors are reviewing logs. All of them paying attention so that you don't have to. Think about the chain of trust that makes this possible. You trust the miners who dug up the ore. You
You trust the engineers who designed the centrifuges. You trust the metallurgists who forged the pressure vessel. You trust the operators who manage the control rods. You trust the inspectors who check the welds. You trust the regulators who oversee the inspectors. You trust the scientists who calculated the physics. You trust the instruments that translate the invisible into the legible. A chain of trust stretching from the mines of Kazakhstan to the plug in your wall, from the equations on Meitner's envelope to the LED that glows in your hallway, from the graphite bricks of Chicago Pile 1 to the concrete walls of a containment building somewhere out in the dark tonight. Every source of energy involves some kind of trust. When you turn on a gas stove, you trust that the pipeline doesn't leak, that the burner is properly adjusted, that the ventilation is adequate. When you drive a car, you trust that the gasoline won't explode in the tank, that the engine will run smoothly, that the exhaust system will carry the fumes away. But nuclear energy asks for a deeper kind of trust, a trust in the invisible, a trust that extends beyond what your senses can confirm, a trust that rests entirely on instruments and institutions and the accumulated knowledge of a century of science. And that trust, imperfect and evolving and never entirely comfortable, is itself one of the great achievements of human civilization. Because it means that we have learned, however imperfectly, to extend our perception beyond the limits of our biology. We have built eyes that can see neutrons. We have built hands that can manipulate atoms. We have built minds, institutional minds made of procedures and regulations and shared knowledge that can manage processes far too complex and far too invisible for any individual to comprehend alone. The invisible fire is not tamed, not entirely. It never will be, any more than regular fire is tamed, any more than electricity is tamed, any more than any powerful natural force is truly under human control. We manage it, we contain it, we use it, and sometimes, rarely but memorably, it reminds us that it is still fire, still capable of harm, still deserving of respect. But tonight, right now, it is doing what it was meant to do, quietly, invisibly, splitting atoms that were made in stars, heating water that will become electricity, powering the world while you rest. Somewhere, a Geiger counter is clicking softly, counting the invisible. Somewhere, a neutron flux detector is drawing a steady line on a screen.
Somewhere, control rods are precisely positioned, managing a chain reaction that began in the equations of Lise Meitner and was first lit in a squash court in Chicago and now sustains a significant fraction of the world's electricity. And deep underwater, in the spent fuel pool of a reactor somewhere, the water glows faintly blue. Cherenkov radiation. The one moment when the invisible fire shows itself, a blue light from another world, beautiful and strange and quiet. You don't need to watch it. You don't need to understand every detail. You don't need to do anything at all. The invisible fire is being tended. The instruments are being read. The barriers are holding. The people who watch the fire that cannot be seen are watching it tonight, as they do every night, so that you can lie here in the dark and rest. Let the ideas settle. Let the numbers drift away. Let the history and the physics and the engineering dissolve into the background noise of the world, like the hum of a transformer outside your window, or the faint vibration of electricity in the walls, or the invisible warmth of a reactor somewhere far away, doing its quiet, invisible, extraordinary work. Just breathe and let yourself fall asleep. The quiet hum of atoms, the steady pulse of instruments, the watchful eyes of people you will never meet, reading numbers you will never see, managing a fire you will never feel. All of it working tonight, as it has worked every night, for decades, to keep the invisible flame burning steadily, safely, silently, while the world sleeps. That is the invisible fire. That is its story. And now it's yours.